WECC antitrust policy, and the NERC antitrust compliance guidelines. All participants must comply with the policy and guidelines. This meeting is public. Confidential proprietary information should not be discussed in open session. This webinar is being recorded and we will post it publicly tomorrow. By participating, you give your consent for your name, voice, image, and likeness to be included in that recording. WECC strives to ensure the information presented today is accurate and reflects the views of WECC. However, all interpretations and positions are subject to change. If you have questions, please contact our legal counsel. Next, we're going to talk about a couple of the upcoming outreach events that we have happening at WECC. First, WECC's Board of Directors approved a new technical committee structure at their September board meeting. And if you'd like more information on that, I'm putting it into the chat and you can find more information and ask questions there. Next up, on Thursday, October 21st at 2 p.m. Mountain Time, we'll host our monthly compliance open webinar. So we hope you can join us for that. And on the 26th of October, we'll be hosting our reliability and security workshop. That will be held in the digital platform called Huba. I just put into the chat a link for the registration. Links for registration will close on the 22nd. So Friday the 22nd, you'll have to be pre-registered by then. We encourage all attendees to register early and then log into the Huba application. You'll see more information about that on the link I sent out. So you can get in there and interact. The agenda is also available within the Huba app. So if you'd like to take a look at the agenda, it is there as well. And then on November 2nd and 3rd, we'll be hosting our Grid Fundamentals class. And that is from 1 to 5. It's a two-part series, and it is an introduction to the fundamentals of the power grid. So this is for beginners in your office or colleagues. Feel free to pass this information along, and I will put a link for that registration in the chat as well. Next, we'll take a look at today's agenda. We've got a packed agenda. We'll have a quick introduction, and then we'll move into advantages and challenges of high penetrations of inverter-based resources and an introduction to grid-forming inverter-based resources. Then we'll move on to applications of grid-forming inverter resources. We'll take a break. Then we'll have weak grid experiences in ERCOT. Then we'll talk about export stability study comparing grid-following inverter-based resources and grid-forming inverter-based resources in synchronous machines. After that presentation, we'll take another break. Then we'll come back and we'll discuss modeling of grid-forming inverter-based resources and frequency response in a 100% inverter-based resource environment. And then our final presentation, we'll talk about grid-forming inverter-based resources in wind, solar, and battery plants. Then at the end, we'll have about a half an hour for questions. So on our next slide, we'll talk about how we're going to handle the question and answer function today. Again, we'll be taking all questions at the end of today's webinar. We're going to be using the Slido application for this. If you've attended WECC meetings before, you're probably familiar with this. You can use this QR code or join at slido.com using hashtag GFM. And you can put all of your questions into that application. So I'll give everyone a little time to pull out their phones and get a photo of that, and hopefully you can log in and you can put your questions in there. You'll also see within this question and answer application, we'll be able to vote on questions and move questions to the top of the list that you'd like our panelists to enter at the end. So throughout the presentations today, feel free to put your questions in here and we will tackle them at the end of today's workshop. Next up, we'll have an introduction to the workshop. And Steve Ashbaker, he is with WECC and he's the Reliability Initiatives Director with us. Steve, I'll turn it over to you.
Thanks, Travis. If we could go to the next slide, please. Boy, it looks like we got a good crowd. That's encouraging. Just to kind of set the table here before we start, I wanted to touch on a few key initiatives within WECC. For those of you that are or may not be aware, we being WECC, in collaboration with NERC and our stakeholders, we have developed a number of what we term reliability risk priorities. One of those reliability risk priorities is the changing resource mix. The changing resource mix continues to be a focus for the industry and the stakeholders within the West, and it's one that we are dealing with in a number of ways as we continue to approach the carbon-free resource mix and the fact that the integration of more and more energy storage technologies, the challenges that we face, we continue to have efforts in both the activities of the operating committee, the reliability assessment committee within their 3-year work plans, where we've got activities associated with how to deal with the integration of these inverter-based resources, the challenges that we are going to be facing in terms of frequency regulation, voltage regulation, reactive requirements, black start restoration, just to mention a few. We are excited today to hear from each of the presenters today, and I want to just reach out to each of you, and the appreciation to both the ESIG members as well as Debbie. Can't say enough for what she's done to work with each of you and the presenters today, and I just want to say thank you, and I'm really looking forward to this. I think you'll find that this will be an extremely valuable meeting, and look forward to hearing from each of you. And again, thanks for joining. Appreciate it.
Steve, thanks so much for joining us this morning. And next up, we have Dr. Deborah Lewis. She's the Associate Director at Energy Systems Integration Group. Debbie, I'll turn it over to you.
Okay, thank you so much, Travis, and thank you, Steve, and thanks to WECC for hosting this event on grid forming inverter-based resources. Can you go to the next slide? Just real quick, for those of you unfamiliar with ESIG, the Energy Systems Integration Group, we're a nonprofit educational organization that addresses technical challenges for grid transformation. So we hold webinars, we organize task forces, and produce reports. We're this month holding our fall technical workshop on Tuesday and Thursday afternoons. It's all free. Just go to esig.energy. You can register for the sessions. Also, we're part of a global power system transformation consortium where we're working with 6 leading system operators around the world, including CAISO and ERCOT, on technical challenges of the evolving resource mix. So if you go to the next slide, today we're going to be talking about system stability. What happens in the seconds or minutes after a disturbance, like if you lose a big generator or you have a fault on a transmission line? Is the system reliable? That is, can the system recover and get back to normal operating process? That event could happen at any moment, at any time of the year, so planners need to look at snapshots of the system. And it's important to note that you can have a moderate annual average of wind and PV on your system, and that can result in a moment during the year with a high instantaneous penetration. And that's what this graphic on the right is showing from Excel. The green bar is showing 25% annual average wind and solar penetration across the year. But you can see the yellow monthly averages can be higher or lower than that. And the blue hourly instantaneous penetrations can go down to 0 or can be up past 70% at one moment in time. So if you go to the next slide, why is this a concern? Wind, PV, batteries, fuel cells, flywheels, supercapacitors, a lot of new resources, all connect to the grid through an inverter. We call them inverter-based resources, IBRs. And this is a highly controllable, configurable power electronics box that you can program. And there's some advantages of these, right? You can get really fast responses. You can ride through long transmission faults that might otherwise trip a conventional synchronous generator. On the other hand, today's grid following inverter-based resources, they don't provide inertia, they don't provide system strength. Now, conventional synchronous generators, your coal, your gas, your hydro plants, they provide inertia, they provide system strength. And while they have controls, their dynamics are dominated by their physics, as opposed to the IBRs, which are dominated by how you program them. Now, grid forming inverters are a promising technology to get the best out of both of these worlds. And that's what we're going to talk about today. So if we go to the next slide, we have an all-star set of speakers here today. I'm really excited. Jason McDowell of GE, that's our reliability working group. He's been at GE for a couple of decades now and has contributed to NERC, IEEE, IEC standards and grid codes. You go to the next slide. Dr. Julia Manabosian of ERCOT. She leads industry efforts, including CGRE working groups, NERC's IBR performance working group. She leads our task force on high penetrations of inverter-based resources. If we go to the next slide, Nick Miller at Hickory Ledge recently retired after 3/8 of a century at GE. He's internationally known for his long experience and research in power systems. If you go to the next slide, Dr. Deepak Ramasubramanian of EPRI. He's one of the stars of the next generation of power engineers. He's already well known for his IBR modeling and stability work. And if you go to the next slide, last but not least, Sebastian Kelly of GE. He's the brains behind making some impossible projects work. He works on integration and interconnection of some very difficult projects. So we're really pleased that these folks were willing to put together these presentations, and we hope this is a very useful event to all of you. And don't forget to go to slido.com and use Cheat FM to ask your questions. Okay, with that, I'll turn it back over to you.
Great. Debbie, thanks so much. That was Steve Ashbaker with WECC and Dr. Debbie Liu with ESIG. Next up, we'll have Jason McDowell joining us. He'll be talking about advantages and challenges of high penetrations of IBRs and an introduction to grid forming inverter-based resources. Jason McDowell is with the GE Energy Consulting, and he's the Senior Technical Director there. Jason, I'll turn it over to you.
Excellent. Thank you, Travis. Thank you, Steve. Thank you, Debbie. It's certainly a pleasure to be here, and wanted to, again, extend a great thanks for hosting this event today. Really looking forward to the dialogue. WECC and ESIG working together on these very subjects it's a timely subject and set of subjects to talk about. So as Debbie pointed out, we are in a transformation in our grid, right? We're in a transformation in our industry, diversifying the supply, taking more energy from variable energy, inverter-based resources, renewable resources like wind and sun, and the characteristics of how that operates on the grid is more dominated, as Debbie said, by power electronics and program controls. And we're going to talk over the next several hours about some of the new technologies and deployment of those technologies on how it can most effectively support the grid as we increase the diversity and increase the penetration of inverter-based resources. So next slide, please. So some key points we'd like to start out with, and you're going to hear this all the way through the next several hours by all of our speakers, is that grid strength is a more urgent problem than low inertia at this point, especially in an interconnected system like WECC. The grid strength, and you're going to hear this a lot, is going to be based on integrating large pockets of inverter-based resources and how to get those inverter-based resources to remain stable in terms of their control and interoperability with all of the resources integrated throughout the grid. Export stability is a more urgent problem than low inertia as well. And Nick, particularly, and Julia will talk about the export capability of taking a set of inverter-based resources in one area and transporting that across the grid stably and reliably. And again, it's primarily based on how the interoperability of those controls interacts with all of the rest of the power system to make sure you can maintain the stability that you need. Performance of inverter-based resources obviously is critical. IEEE P2800 is one of the latest interconnection standards that is under development right now that is tackling this. So certainly adopting the good work and some of the requirements that are in IEEE P2800 is a best practice, and also interfacing with OEMs with how to deploy the existing and new technologies is a big deal. But the big message is the sky is not falling. Yes, things are changing. We do have good, solid, available solutions and processes in place, but it's a matter of scaling them in order to deploy the technology in ways that matter for the grid. IBRs are different from synchronous generators. That's important to note, but how to deploy them is also critically important. That's what we're going to talk about today. So next slide, please. Okay, let's set the stage with what we're talking about with grid following versus grid forming inverters. Most of inverter-based resources, as Debbie said today, are grid following. That means you need to have a grid available there to synchronize to. A voltage reference is needed for inverter-based resources to ultimately decide how to fire the inverter controls, converter controls, and inject a controlled current under all operating conditions, normal conditions, under disturbed conditions. And these current regulators drive the performance. And as grids get weaker, it is more complicated and more difficult for the current regulators to maintain their stability. There are certainly a lot of tricks and tweaks that can be made for this, but that's where the grid forming inverter can come in to help manage a lot of the stability concerns about the control in weaker systems. For grid forming, it's different than grid following is in that there's no reliance on external grid voltage to generate power. It actually can generate its own voltage reference and quickly stabilize the grid by adjusting a voltage reference and frequency in order to deliver its power. There are many different types of this type of control topology that's being implemented and considered. We're going to talk a lot about that today. But grid forming resources can fundamentally operate without or very few synchronous machines electrically nearby. Next slide, please. Okay, and this is just a comparison of how grid forming, grid following, and synchronous machine resources compare. There are a lot of functions that are common between all the resources, as you can see here in the center of this Venn diagram. This is a good time to point out that a little bit of a teaser here. There's an IEEE magazine article in the IEEE PES Power and Energy magazines coming out very soon at the end of this year. That's going to be talking a lot about the concepts that we're going to hear in this workshop. Just wanted to plug that. Julia had led the article, Nick and Deepak and I had contributed to the article. So a lot more will be explained in there. But closed loop voltage control, fast frequency response, primary response, balancing, and stability services are certainly all possible coming from all IBRs, whether grid forming or grid following. But grid following controls, again, primarily use a controlled current injection and requires a minimum grid strength to be stable, as opposed to grid forming and synchronous machines have voltage persistence and inertia to support grid stability during the disturbances. Also having capability of black start and island operation as well. Next slide, please. Okay, so let's talk a little bit more about technology transitions for IBR stability. This is probably something that you've seen in a different form. Migrate put together a transformation slide about technology. And this is a new neat way that Nick had actually put together to look at where we are and where we're going. So what we're seeing here is the relative power system stability as more advanced technology is being deployed. So we have been on a track to make the best use of grid following controls that we have been, and trying to deploy those controls in the state-of-the-art equipment, from wind to solar inverters to batteries. and other inverter-based resources to make the best out of the controls, how they operate, how they're stabilized in weaker systems. But in order to really get to a integration of high penetration of inverter-based resources, getting with effective short circuit ratios, less, approaching 1 and even less than 1, we need a transformation. We need a paradigm shift. And that one of the big aspects of the paradigm shift is the implementation of grid forming controls and allowing the stability to really manage a lot of the weak system issues that we experience in terms of control stability with grid following controls. So with grid forming controls, they certainly help. They're not a silver bullet. We need to look at other reinforcements as well, as Nick and Sebastian and Julia are going to talk about relative to stabilizing power transfer. But these types of controls really go a long way to providing stability where we're at the cusp and perhaps at the maximum capacity where grid following controls really can't be improved anymore to keep the stability of the grid. So next slide, please. Okay, you've seen this slide probably dozens of times so far, but just wanted to use it again to understand what we're really talking about in terms of inverter-based resource performance to support frequency versus other conventional resources. So obviously, what we're really concerned about is maintaining the system frequency, maintaining the synchronous machine speed during disturbances, maintaining the balance of energy coming into the grid versus what's going out of the grid under all time frames. If we lose a large generator, obviously the imbalance of instantaneous imbalance causes the electrical frequency to drop. The rate of change of that drop is dominated by the synchronous inertia by synchronous machines. It's also dominated by the energy injection coming from inverter-based resources and fast frequency response. And it also is going to be dominated by the new energy injection from grid forming controls. So the more you can inject, the quicker you can inject that initial decline and eventually coordinate with the primary frequency response of governors in conventional and the active power control in inverter-based resources to recover the frequency and automatically balance things out. We're going to be talking a lot about that initial decline and how we support the frequency in the first several seconds and coordinate that with the primary response and recovery over tens of seconds in this talk. But coordination of all of those capabilities is critical in order to actively support the stability of the grid. Deepak will talk a lot about the coordination of this control as well in his talk. Next slide, please. Okay, so here, I'm not going to go through every single one of these columns, but wanted to set the stage of how the different technologies support grid inertia and fast frequency response as well. A quick time check. Obviously, synchronous machines, as Debbie pointed out, have an inherent physical response because they are synchronized to the grid. And if there is an instantaneous change in frequency because we lose generation or we have even a loss of large load, the frequency moves around, and the coupling of the inertia in a synchronous machine is direct to the grid because of the synchronizing torque of that machine. A drivetrain that is in motion is staying in motion. Oops, I'm getting an error on my, here we go. I'm sorry, I'm getting an error on my PC here. So an object in motion tends to stay in motion. But inverter-based resources don't have direct coupling of inertia onto the drivetrain, from the drivetrain onto the grid. So there is no inherent response, but it needs a controlled response that is put in place that can inject energy at the right time period to arrest the initial decline. The fast frequency response is one of those controlled responses that injects an initial amount of energy into the grid to help arrest that decline. It's in itself, it is somewhat mimicking the amount of energy functionally that is given by synchronous machines, but it doesn't directly couple the energy like a synchronous machine would automatically onto the grid to arrest that initial decline. As opposed to the new grid forming features and grid forming controls, there are several levels of performance that can be achieved with those grid forming controls, but that control itself is intended to replicate synchronous machines and support that initial frequency deviation once an event happens. So that's the difference between a synchronous resource and various levels of inverter-based resources that, that can support frequency. We're starting to see requirements of these types of features and functionality from inverter-based resources. Fast frequency response, for example, is required in Brazil, in Canada, in Australia, in Ireland, in Great Britain, and in Texas in various forms. Some have market mechanisms that's coupled as well to help pay for those services, some don't. With grid forming features and requirements, there's no market mechanism today. There are a few special applications that batteries have applied for black start, for example, that are trying to drive some of the requirements. There is a draft voluntary requirement in Great Britain called GC 137 that is going to be put in place. It's being balloted right now to update the National Grid Code. But by 2025, we're expected to see more grid forming and grid following requirements in North America because of P2800, and also in Great Britain, and so Australia, Germany, and maybe even Texas expect that more of these requirements will be put in place and adopted. Next slide, please.
Jason, you've got 13 minutes left.
Thank you, Debbie. Great, I think we're right on time. So this is a chart that identifies some of the various levels of frequency stability risk. And actually this came out of the IEEE article that we had written. Nick and Julia had really pulled this together. I think it's a really nice way to look at this, where the frequency stability risk is really dependent on a bunch of things. First and foremost, how big is the system, right? Are you very largely interconnected? Do we have, lots of inertia on the grid that we can count on? Do we have lots of headroom available from resources to be able to support and recover the frequency? So we have categorized frequency risk based on occasional risk. Generally, that is more synonymous with larger interconnected systems like WECC. We have acute frequency risk that has frequency control concerns that might be able to limit operations some of the time under certain system operating conditions. And the control of frequency is possible, but it needs to be planned. It needs more work to understand how all resources can work together interoperably, especially during system splits. And then chronic frequency stability risks are in typically more smaller systems, more islanded systems that have substantial frequency control problems and high rock off because the system really is moving around a lot more. There's simply less inertia. There's less resources that may contribute to frequency response. And those systems are the islanded systems like Great Britain, Australia, AirGrid in Ireland, and Hawaii. Grid forming controls can provide quick inertia-like response and support the frequency with equipment limitations. Talk a lot more about that. But it's a matter of coordinating that control and using it effectively with all the other controls that are online and available at that time. So next slide, please. Okay. Let's talk about a different subject. We talked about frequency so far. Let's talk system operation in weaker and weaker grids. So I think with this audience, we don't have to spend too much time to define what a weak grid is. Fundamentally, though, the big takeaway is that weak grids are relative based on the resources that are being integrated in any particular area. You can have a strong grid historically maybe 300 to 345 kV, maybe 500 kV, and you put in and install a whole bunch of inverter-based resources, and maybe retire some conventional plants with synchronous machines, and all of a sudden that historically strong grid can become very weak, depending on the amount of inverter-based resources that you have. So this cartoon that's up here that Nick has been using for years, with a strong grid being a solid, thick tree that's being influenced by an individual plant where the puppy dog is trying to pull it over, the strong grid is not going to move around nearly as much. The sensitivity for voltage to the influence of one plant is not going to really influence the grid all that much. In a weak grid, you have high influence over many plants, many inverter-based resource plants that can highly influence that grid to move around. Voltage and frequency could highly fluctuate in weak grids, and there's a lot more sensitivity in terms of stability of the inverter-based resources, perhaps going unstable. So strong grid, the controls can be fast and stable, but designing controls for weak grid is more like running on ice, right? That we need to slow down, we need to be more careful, we need to make sure that the controls are stable and recovering in a way that we're not pushing the grid off. The weak grid conditions are slippery, right? We're not pushing the grid into a mode where things are going to fall apart. There are ways to resolve weak grids. Certainly, coordinating controls from inverter-based resources and deploying grid forming controls can help in a big way. Also, providing reinforcements from synchronous machines, including condensers, gas, hydro, nuclear, as well as reinforcements from transmission can also strengthen grids in a particular area. But really the focus is on interoperability between the resources to maintain that stability and so that the controls can be stable. Okay, next slide, please. Okay. A lot of words on this slide, a lot of plots. The main takeaway is that there's a lot of different ways that the inverters or converters can go unstable. Failing to ride through disturbances, converter control interactions, instabilities, cycling between control modes, and steady state transfer as well gets more challenging. But in all of these plots, with all of these problems, you see that you have a non-constant voltage. You see that there's a lot of fluctuations in voltage over time. And this is the challenge in trying to make weak grids stable with inverter-based resources. Again, we have solutions to this, but those solutions need to be identified. Those risks need to be identified upfront, and technologies can be deployed in projects if it's done properly and deployed with the right controls and the right mitigations at the right time in the project. So a lot of it has to do with identifying the right solutions in the interconnection process and deploying them. Next slide, please. Okay, so just to wrap up, a couple of slides here, again from the article, looking at some of the voltage and angle stability risks that we have to be cognizant of. And again, we look at highly interconnected systems where those voltage and angle stability risks tend to be localized, where local electrical disturbances may have a risk of a pocket of inverter-based resources, perhaps going unstable, perhaps causing voltage and frequency issues to interface at that local level. But on a broad basis, it's not a broad grid problem where it affects the entire interconnection. And that's certainly where WECC is right now. But we need to watch out for those local issues where we're integrating large pockets of inverter-based resources. And then there's regional stability risks and system-wide stability risks as the grids get weaker, as they get more compact, and especially islanded systems, where you'd have more wholesale angular separation across the grid. Nick is going to talk a lot more about this in his talk, where it's a lot more important to understand how voltage stability and angular separation can start and propagate in grids that are islands. Next slide, please. And then finally, control stability risks, independent of the voltage and angular stability risks, also are localized, are regional, and are system-wide. And in both of these cases, properly configured grid forming or grid following controls can mitigate most stability risks. In the case, in the previous slide, I forgot to mention, for angular and voltage stability across the network for transfer, those grid forming and grid following controls can mitigate some control stability risks, but you still are going to need other reinforcements in order to mitigate the balance of those controls, of those angular stability risks. But fundamentally, again, large interconnected systems have localized control stability risk. And as the systems get smaller and weaker in islanded systems like in Australia and Hawaii, it becomes more challenging to keep the entire system ultimately stable and having all of the resources be interoperable and avoid all of those periods of instability like we saw. So with that, I think we might have time for maybe one clarifying question. I'll turn it back over to you, Debbie.
You have 4 more minutes, sorry, if you need it to take it.
Okay, no, I think that's it. I'm done with my section, so if there are any questions, be happy to answer them. If not, we'd love to turn it back over to you, Debbie.
Okay, well, I do see some questions in the Slido, and we're just making clarification questions at the moment. And Travis, do you want to address the first one about slides and recording?
Yeah, absolutely. So the slides will be posted to WECC.org. I'll provide the link. They're being uploaded right now as we speak. So we will provide that once that becomes available. And the recording of this workshop will be available on WECC.org as well, but that won't be until tomorrow morning.
Okay. So there is a question about the cost of grid forming versus grid following inverters. And Jason, I don't know if you want to take that or if you want to give that to Sebastian at the end to take.
Yeah, I think as we go through this, we can certainly weave that in. The overall cost of the equipment is very minor compared to relative to the overall cost of not being able to, the overall cost of the instability that might occur in the grid if we did not manage this, right? So it's all relative, but let's hold off and answer the cost question as others go through their pitches about the deployment of grid forming resources. Okay,
and the second question is inertia an issue related to IBR controls alone, or is it related to the non-dispatchable generation resources that are behind the IBRs?
Okay, that's a good question, and that's something that others will address here too. But it's not a concept that's relative to IBRs alone. Inertia is fundamentally the coupling of the synchronizing torque and the rotating mass of synchronous machines together with the energy injection that's given by inverter-based resources to arrest that initial decline. So the name of the game here is how do all of the resources work together during a system event to arrest that initial decline and providing the appropriate amount of energy and coordinating with the later layers of control with primary frequency response, governor response, and eventually balancing the system out. The comment about the non-dispatchable is not relevant in the initial time frame, but it can become relevant later in recovering the frequency in later time periods about how the system is dispatched, redispatched after an event, and how the frequency recovers in the many tens of seconds to minutes time frame.
Right. We could have a system with just fuel cells and batteries, and it would have zero inertia.
Correct. And honestly, that's one of the aspects that we're really talking about is as we have more inverter-based resources, what does a frequency event look like? And what does frequency response really need to do to maintain, equipment capability, to maintain the integrity of the grid? Can we have frequencies that deviate more in the future with more inverter-based resources or not? That's all a discussion and a debate that we will have and that we are currently having as we integrate more inverter-based resources.
All right. Thank you, Jason. That was all the questions.
Great. Thank you. I'll turn it back over to you, Debbie.
I think
Great.
Travis.
Great. Jason McDowell, thanks for joining us this morning. That's Jason McDowell. He's with GE Energy Consulting. He's a technical director there. His email is up on the screen, so feel free to reach out should you have more questions for him, or he will be on the line at the end of today's workshop to answer the questions that are put into the Slido. So feel free to use your phone or go to slido.com, #GFM, and you can ask questions there. Next up, we'll be discussing applications of grid-forming inverter-based resources with Dr. Julia Matavosian of ERCOT. She's a lead planning engineer there. Julia?
Good morning, everyone. And we can go on the next slide. All right, so what I'll be presenting right now is based on a survey that I have done of actual applications of grid forming inverters around the world. Obviously, none of this work is my own, so I have lists of authors or people who participated in implementation of the projects or provided me with information about the projects that I'll be talking about. And also a disclaimer, this work is not something that we currently do at ERCOT, so all of the applications are from elsewhere so far. Next slide, please. So just an outline of what I'll be talking about today. There is a number of battery storage systems in microgrid applications and used also for black start of simple cycle gas turbines. It is implemented by GE. Then I'll talk about battery storage project supporting an island with at times 100% inverter-based resource penetration in St. Eustatius Island, implemented by SMA. There's a Loch wind farm in Scotland. This is the pilot testing that took place a couple of years ago done by Siemens Gamesa. Mackinac back-to-back voltage source converter for HVDC flow power control. Sorry, HVDC flow control projects done by Hitachi ABB. Drimple battery storage project in Australia, again by ABB. Hornsdale battery storage in South Australia by Tesla. Some more grid forming projects underway in Australia, and then I have a brief slide just talking about what drives this pilot projects so far, and then jump to conclusions. Next slide, please. So let's start with the first one. GE, as I mentioned, has a number of projects using battery storage, grid forming battery storage in various applications. The oldest being Katla community in Alaska, where the battery is used there to power up a microgrid for the community. And so it's a relatively small project, but it's also probably one of the first ones for microgrid application was implemented relatively early on. Then Vernon in California, and there you have 5 megawatt battery storage powering up, providing security of supply to industrial load there. So at times it operates as grid connected, and at times it powers up island with that industrial load isolated with grid forming battery. And then the rest of the projects on the list, they're used for black start. So this is where battery storage is used to black start heavy duty gas turbines. So initially, those were powered by, were started up by diesel, and then the gas turbine is becoming effectively black start unit for the rest of the grid. But because of some environmental constraints, emissions constraints that these gas turbines were facing, they were looking for alternative solutions instead of using diesel. And that's where grid forming batteries were implemented. So grid forming battery initially is starting up these gas turbines, and then gas turbines are becoming effectively black start units that can participate in black starting of their parts of the grid. Addition of these batteries didn't require large changes in the existing plant, so it was only about implementing the battery and appropriate controls. And soft start is used for a grid forming battery to avoid large inrush currents at motor energization and transformer energization. One thing I wanted to mention at the bottom of the slide, GE together with NREL, First Solar, a number of other academic and industrial partners are participating in DOE-funded CITO project on advanced grid forming inverter controls, modeling and system impact study for inverter-dominated grids. So this is a project that's looking at development of grid scale grid forming inverter controls, and also the plan is to conduct a number of studies on large scale systems to see how grid forming inverters impact the grid. Next slide, please. I was trying to control it myself. So the next project is St. Eustatius Island. There is a number of island applications that SMA has implemented, but this one is more widely publicized. So this is an island with about 2.3 megawatt peak load, 14 gigawatt hours yearly energy consumption. It was initially powered by 9 diesel gensets, 4 MVA, and then later on 4 megawatts of PV. Were installed. Again, in the later stage, grid following battery was added, followed by 2 grid forming batteries. So currently there is a common plant controller that sends start-stop signals to gensets, does frequency and voltage control during genset 3 operation, and then transfers frequency and voltage control to genset controllers when gensets are running. It can do load distribution between 2 parallel grid forming inverters without any external communication. They've tested diesel off mode, initially just in test environment, but now they regularly operate during daytime with diesel being off and the grid being powered just by solar and backed up by storage. There is seamless immediate load transfer after generation contingency, and they had actual contingency on the grid with simultaneous loss of all gensets at peak load, and the frequency dip was 0.6 hertz, and restored. The frequency was restored back to normal within 3 seconds, and no load shedding happened. There have been also several real-life testing of voltage ride-through capability during various faults and operating modes. So this is kind of a successful island application of grid-forming batteries and 100% inverter-based grid, even though small. Next slide, please. All right, so next one is testing of existing Siemens Gamesa wind turbines in grid forming modes. After initial pilots on smaller sites, Siemens Gamesa tested 23 direct drive full converter wind turbines. Total installed capacity of that wind farm was 69 megawatts. They basically reprogrammed controls of existing wind turbines to operate in grid forming mode for 6 weeks. Between May and June 2019, and that took place in Scotland. They used the virtual synchronous machine control method for grid forming control. As Jason mentioned, grid forming controls can be implemented in different ways. To be fair, all of the applications that I'll be talking about today, they all went for using virtual synchronous machine control method. And that mainly probably has to do with, synchronous machine behavior being more familiar and kind of trying to replicate that with grid forming inverters. They tested different inertia constants. So in virtual machine mode, there is a swing equation is programmed in, and inertia constant can be changed, and depending on the storage or energy buffer available behind inverter, there is some flexibility there in changing inertia constant. So they tried different inertia constant settings. They survived 6 large under frequency events that happened on the grid during testing period. The largest one had up to 11 hertz per second, 110 millihertz per second rate of change of frequency, and frequency drop by 0.5 hertz. Additionally, they wanted to simulate larger frequency event with rate of change of frequency of 1 hertz per second. So this is the requirement that GB is heading towards, and frequency deviation of 3 hertz. And they tested it with inertia constant of 8 seconds on grid forming inverters. There were no significant grid voltage phase steps, and so the largest that they tested at was 0.2 degrees. The wind plant was able to respond to all events autonomously and immediately with power injection as expected, with inertia constant as configured. They didn't have turbine trips due to stalling, overpower, overcurrent, or during all of these grid events. One thing I forgot to mention is that they were using rotational energy of wind turbines as energy buffer to tap into when they needed to provide active power injection during frequency events, providing this type of virtual inertial response. So obviously, because of that, turbine's ability to respond is affected by wind speed. And so they encountered several events where wind speed was declining at the time of the response. And so that deteriorated this virtual inertial response from wind turbines. And also wind turbine ability to respond at low or zero power output is extremely low. So this limitations can be overcome by either having small batteries at the site to provide this response in inertial time frame. Right, yeah, that's I guess what I wanted to mention. Next slide, please. Oh yeah, no, the one I wanted to say one more thing. One more thing that they suggested to overcome this limitation is also that inertia constant can be configured, can be changed in real time based on actual wind conditions. So during lower wind conditions, less aggressive inertia constant can be used. I mean, this is challenging from a system operator point of view because you have changing inertia constant in real time, but this is a flexibility that's there and that is not there with, say, synchronous machines or synchronous condensers. Next slide, please. Now I'm ready. All right, so this test continued in August-October timeframe of 2020, where they successfully demonstrated island operation of that same wind farm, as well as black start of the wind farm with successful re-energization with the rest of the grid. So in the island mode, they were able to autonomously operate a wind farm as an island. So basically just powering up auxiliaries of the wind farm and keeping output from the wind farm relatively low for that. And then they tested initially starting from all wind turbines operating in grid forming mode and successively decreasing amount of inverters that were in grid forming mode just to see how many do they need. They actually went down to all the way down to 1 wind turbine in grid forming mode, but said that they were able to reach stable operation with 2 of wind turbines operating in grid forming mode. They also tried connecting 7 megawatt load bank to the island and powering up the island that had some load in it, and were also successful with that. Then to do black start, they equipped 4 wind turbines with small diesel generators, 125 kVA each. Just to put it into perspective, the turbines are 3.4 megawatts. They could have done this with battery as well, but diesel was kind of faster to test, and that was just a proof of concept, that it's possible. They needed diesels to power up auxiliaries of this for grid forming wind turbines so that they can start up, and then in grid forming you will power up the rest of the wind farm. And so then once they started these 4 wind turbines, powered up the entire island, they re-energized 132 kV switchgear and 132 to 275 kV transformer, and then resynchronized with the grid successfully. Next slide, please.
Julia, you've got 13 minutes left.
13?
Yes.
Yes, okay, should be good. All right, so this project I just recently found, looking at, grid forming applications, was a bit surprised that I haven't heard about it before. I guess that has to do with that this is kind of a grid application. This is not a resource, and it's more of a fax device that was installed. But if you look at it, you can say that is a grid forming application as well over there. What are we talking about here is Hitachi ABB 200 megawatt bidirectional back-to-back HVDC light converter station that was commissioned in 2014 to help control power flow and enhance grid stability and support integration of additional IBRs. And this is on Michigan's Upper Peninsula near Strait substation. Basically, at the Upper Peninsula, the grid is relatively weak, and they were seeing more inverter-based resource coming into the grid, and that basically forced the power flow along long transmission path towards south, Lower Peninsula, where most of the load is connected. And also the connection of the Upper Peninsula is relatively weak to the rest of the grid, and there exists possibility of disconnection on the Upper Peninsula side. And so previously the grid was supplied through 238 kV lines from the Lower Peninsula. And so what they did now is installed that HVDC light converter station. This converter station was selected over the classic HVDC technology to provide better voltage and reactive control, provide stability in weak grid conditions, provide power oscillation damping, governor-like frequency control, and also support island operation. It also has black start capability. So for black start capability and for frequency control, it is using the lower peninsula side of the converter as an energy buffer. So it basically takes energy from the Lower Peninsula and to power up that islanded part of the grid during island operation and to provide frequency control. And south side converter is connected to the strong side of the grid, and therefore they used current controlled converter station there. So as I mentioned, north side converter connects to extremely weak part of the grid. And so I just took that phrase from the article that describes this project. And so it says phasor voltage control was developed based on direct control of converter's internal AC voltage amplitude phase. And so if you read this definition, that's actually what goes into definition of a grid forming inverter. And that's why I picked up this project to have in this set of grid forming inverter surveys. So it does act as a grid forming inverter in this application. So next slide, please. So Hitachi ABB Energy Storage in Australia, there is a number of applications. I don't recall if all of them are by ABB in microgrids where grid forming batteries are powering up power supply of coal and iron mines in Australia. There are maybe 3-4 projects like this, but this is the largest grid forming project right now that's grid connected. And so it can operate in grid connected mode as well as just powering up an island grid if the connection to the rest of the Australian grid disconnects. They use virtual synchronous machine control method as in all other applications. The battery is 30 MVA, 8 megawatt hours. It is connected at the end of the long radial line that goes into Australian grid, 132 kV. It has 91 megawatt wind farm nearby, local load of up to 8 megawatt, and 2 megawatt of local rooftop PV. And so, as I mentioned, if the connection to the rest of the grid trips offline, the grid-forming battery can power up that island and therefore maintain reliability of supply to the island load. And so in the first 6 months of operation, it reduced loss of supply in this area from 8 hours to just 30 minutes. And we can go to the next slide, please. All right, so this battery is designed to provide a number of functions. It can provide virtual inertial response of 2 megawatt seconds, I think is missing here, with configurable magnitude and slope. So again, here, as opposed to synchronous machine, inertia constant can be configured, and also shape of response can be configured as well if needed. This allows to reduce rate of change of frequency after sudden loss of generation and deliver that arresting power that inertia of synchronous machines is doing today. This is different from fast frequency response, as this response is nearly instantaneous. It can operate in low short circuit ratio down to less than 1.5. It's also able to provide system strength support with short overcurrent capability of up to 2 per units for 2 seconds. It can, as I mentioned, do island operation utilizing virtual inertia, and has also primary and secondary frequency control over there. Additionally, what it can do, it can adjust frequency of the island to go up when there is over generation conditions in an island, because you can imagine they have 8 megawatt peak load connected together with 91 megawatt wind farm, and then 2 megawatt of rooftop solar, as I mentioned. So what it can do, it increases frequency of the island, and that makes distributed rooftop solar trip offline, so that way it can control the power production. It has black start capability, so it can start that islanded grid and then re-energize with the rest of the grid, also using this soft start method that I talked about before. And that's not very much related to this battery being grid forming. Grid following battery could have done this as well, but it's participating in the special protection scheme, where if interconnector from South Australia to the rest of the grid trips, and interconnector is 500 kilometers away, it actually, the battery will provide very fast frequency response to support isolated South Australian grid, to provide part of the support. It's not the entire scheme that they have there. Next slide, please.
Julie, you've got 5 minutes left.
Good, I'll go fast. So Tesla Hornsdale battery, you probably heard about that one. It used to be the largest battery in the world. 100 days, 100 megawatts were built. Initially, this battery was built as grid following, expanded to 150 megawatts last year. Currently, they are testing 2 inverters in virtual machine mode. So this is also a mode that that is designed to provide inertia-like response and provide reactive support as well. So they actually real life tested this project when a nearby coal plant tripped at the end of May this year. And so what you can see on the right hand side here, the top graph shows the response of the entire battery plant. So the plant has 2 inverters that are in grid forming mode, and then everything else is grid following. And overall response of the plant looks like a frequency response, governor-like response, if you will. But then if you look at the bottom chart, you can see response of these 2 inverters that were in virtual machine mode, as Tesla calls it. And so you can see that response more reminds you of inertial response from synchronous generation, because it's coincidental with the frequency decline. So it's at the same time, and it peaks even before the frequency nadir. Next slide, please. There are more grid forming batteries underway in Australia. I will not read through the slide. You can go back to this and see. So, but basically the message here is the commercially available technology is there. They're building, but currently there is confusion or a lot of uncertainty about how the requirements will look like for provision of inertia or system strengths in Australia. And so some of these battery storage projects currently are building to operate in grid following mode, but are future proofed to be converted to grid forming mode if there is some kind of incentive or clear technical specifications of what they're actually supposed to do. Next slide, please. So some of the drivers behind this existing projects that I talked about, in Great Britain, they started Stability Pathfinder project. So this project looks to find short circuit strengths contributors and as well as inertia contributors in certain locations on Great Britain's grid. So the first phase of the Pathfinder was actually limited to conventional technology, and they procured all of it from synchronous condensers. Pathfinder phase 2 and 3 is open to inverter-based technologies as well. And so theoretically, grid forming inverters could participate, and this could be viewed as an incentive for those. In parallel, Great Britain has developed minimal specifications for grid forming capability. So this is currently in the stakeholder process for review, and they expect this to be finalized by the end of this year. So this is basically like a grid code requirement for grid forming capability. This is not going to be mandatory requirement, but they are rather looking to have a market product to incentivize this grid forming behavior. And then Pathfinder is basically a way to explore capability of these technologies in a smaller scale before full-blown market for some kind of grid forming service is implemented. And so for Pathfinder stage 3, phase 3, the requirements, technical specifications for the projects are actually based on this minimal specification that I just mentioned. In IEMO, there is a requirement for inertia and system strength provision in certain parts of the grid. This has to be procured by a transmission distribution service provider, and so this also can be viewed as an incentive for grid forming inverters to participate and provide this service. IEMO also just recently released Advanced Inverter White Paper, where they identify grid forming inverters as a needed component going forward and implementing more inverter-based resources on the system. And they propose gradual approach where grid forming inverters are implemented on the grid, helping local parts of the grid first, but then gradually using this capability wider and then providing black start at the end, at the final stage. Hawaii Electric Wide PSCAD studies report that was recently released also recommends requiring grid forming inverters in new battery storage in the future projects. And we can jump to the next slide and I'll go through conclusions very quickly. Sorry, Debbie. So there is a handful of applications of grid forming inverters around the world today, so not many. The applications are primarily small and microgrid applications. More connected grid forming batteries, grid-connected grid forming batteries are on the way in Australia. Stability Pathfinder in GB is encouraging more grid-connected utility-scale grid forming projects in Great Britain. One thing I just wanted to point out is the battery, grid forming batteries, the low-hanging fruit for grid forming applications. There are large amounts of batteries currently in interconnection queues in some systems around the world. And this is a really good window of opportunity that should be seized for future-proofing paths forward with higher shares of inverter-based resources. Thank you, Debbie, and I'm sorry I went over time.
Oh, no, that was awesome. Thank you so much, Julia. Travis, could we just do a couple questions real quick?
Absolutely. Let's do a couple of clarifying questions. I'll let you tackle that.
All right. So first of all, someone asked what rock-off is. Rock-off is rate of change of frequency, how fast frequency falls. Someone else asks, are IBRs with GFM capability available today? Obviously, you just showed that some are, but I think what they're asking is it commercially off the shelf?
So capability is there. I wouldn't know what commercial off the shelf would mean today because there is no, the first grid code requirement is still in works. But so from this projects that I've seen, all of these are kind of custom tailored to some particular application. So there is no off the shelf available. Functionality is there, but it has to be tuned and adjusted to what's required at the specific location today.
Okay. Thanks, Julia. I think probably we should stop and do our break now, Travis.
Great. Yeah, that sounds great. Thank you to Dr. Julia Matavosian for joining us. She'll be joining us after the break when we come back. So let's take a break and we'll come back at 20 after the hour. Again, thanks for joining us for WECC's Grid Forming Inverter-Based Resources Workshop, and we'll see you back here at 20 after the hour. Time is 10:20. Megan, if we can go to the next slide, please. We will be taking all the questions this morning into the afternoon on slido.com. You can join on your computer by going to slido.com and using the event code #GFM, or by scanning the QR code with your cell phone. Right now, we'll give you a moment to do that, and you can pull up slido.com where you can ask your questions on that application. You're also able to vote on questions that others have asked, so you can bump them to the top. So we're sure that we can get to those more popular questions. And Julia, are you back from break?
Trying to start my video. Okay.
All right, there you go.
So let's
Megan,
just
we'll
continue.
Go to the next slide.
We can go to the next slide.
We'll continue with Julia Matavosian of ERCOT. Julia, take it away.
All right, we can go straight on the next slide. So I'm switching gears here a little bit, and I will not be talking about grid forming inverters for the next 30 minutes, but rather talking about issues that grid with high concentrations of grid following inverters in certain parts of the systems can experience. And this is based on ERCOT grid. So just to provide a little background, you probably all know, but just put it into perspective. ERCOT grid is not synchronously connected with the rest of the US. There is only a small number of DC ties that amounts to about 1.2 gigawatts altogether. And our system is peaking at about 75 gigawatt in summer, the summer peaking system. And ERCOT operates about 90% of Texas load and covers 75% of Texas land. ERCOT is independent system operator, so we don't own any wires or generation, but operate ERCOT grid and electricity market. Next slide, please. And I can click to the next one right away. All right, so this is a little bit more background on our generation mix, and you can go through the numbers later, but what I wanted to point out here, we're still about 50% natural gas-based generation fleet. Almost 25% of installed capacity is from wind, and then coal share of our generation fleet is shrinking because of recent coal retirements, but on the other hand, solar is picking up. Here you can see it's still kind of low % of solar, but on the next slide, you'll see that we are anticipating much more on our system. Next slide, please. So this chart is showing a historic development of inverter-based resources on our system, as well as what we have in the interconnection queue with signed interconnection agreements. So in a dark blue color here, you can see operational wind generation. This is commercially operational and what we have synchronized with the grid going through last stages of testing before becoming commercial. Then in light blue color, you see planned wind generation with signed interconnection agreements. Again, in dark yellow, it's operational and synchronized solar generation. And then in dark purple, it's operational and synchronized battery storage capacity. And again, light yellow color is planned solar, light purple color is planned battery storage projects. So you can see we have kind of rapid pickup in wind generation over the past 7-8 years. But then now solar is kind of taking over, and we are foreseeing about 10 gigawatts of solar by the end of this year. And then it's 10 gigawatts added every next year if we trust to what's in interconnection queue. These projects are all with signed interconnection agreements, so they are more likely to be built, maybe not all of it, and maybe not across this next couple of years, but we have a lot of inverter-based resource capacity still coming and being planned on our grid. And you can see a relatively big pickup in interest for storage as well. Next slide, please. So this table on the top just summarizes what I just said about inverter-based resources. So we currently have more than, or by the end of this year, we'll have more than 45 gigawatts of inverter-based resources installed. And then by 2023, this is more than 70, like around 75 gigawatts of inverter-based resources in our system. So currently, most of wind and solar generation projects are located in West Texas and Texas Panhandle area. You can see here on this schematic chart at the bottom. This is because these areas are rich in resource, both wind and solar, as well as land availability, what drives those resources in those parts of Texas. So what it results in was long distance transfer to load centers that are in, Dallas, Austin, Houston, San Antonio, so central and eastern part of Texas. And also in these areas, as though there is less consumption there, there is traditionally less synchronous generation in those areas, and also during times when periods of high wind production, high solar production, synchronous generation tends to be offline because of market conditions. And so there are times when this part of Texas basically powered almost entirely by inverter-based resources. Next slide, please. So this is just focusing on one area and kind of provides an overview of what I'll be talking about in more and more detail in the rest of the presentation. So if you look at the map at the top and this square area of Texas map, this Texas Panhandle, and then darker blue areas, nearby Panhandle area. Currently, we have more than 10 gigawatts of inverter-based resources connected in those two areas. These are remote from the rest of the grid, as I said, again, limited to no synchronous generation in the area and long distance power transfer to the rest of the grid. So what we've seen as indicators of weak grid is high frequency oscillation on numerical instability when we try to do dynamic simulations in PSSC. We can see high voltage overshoot or even high voltage collapse during fault simulations right after fault is cleared. And then if we just do kind of screening type of calculation and calculate what's the short circuit ratio, and here you can see weighted short circuit ratio. I'll talk about this term a bit more on the next slides. But basically, if we estimate short circuit ratio for this area, then we see that this area has low short circuit ratio, and that's a sign of weak grid. We tried several improvements in this area, installed 2 synchronous condensers. It had its own, even though it helped with weak grid situation, it had its own stability issues. I'll talk about it later. Another way is to reduce impedance, adding additional transmission circuits, and also some improvements that Jason, I believe, mentioned can be achieved by controls tuning and coordination of controls of inverter-based resources in the area. We can go to the next slide. So this previous slide was kind of an overview of a problem, and now I'll kind of drill into this a little bit deeper. So the ability of power system to operate in stable manner and for the system to recover from major disturbances is influenced by electrical strengths of the system at the point where this equipment is connected, So stronger systems are more tolerant to variations and perturbations occurring within connected plant and recover more easily from major disturbances such as faults or sudden loss of equipment. So, but basically what system strength really characterizes is how electrically far an interconnection point is from strong voltage source. You've probably seen that traditionally short circuit ratio is used to characterize system strength. So this is mainly because if you do short circuit calculation at a given point, it gives you a good idea about how far this interconnection point is from contributors of short circuit current, and that is a good characterization of electrical distance between short circuit current source and the interconnection point that you're studying. And so that's why traditionally short circuit ratio have been used to characterize system strength. And again, the short circuit ratio is a ratio between short circuit contribution at the interconnection point that you're looking at and the capacity of inverter-based resource that you are trying to connect there. And I'll have more about this on the next slide. Next slide, please. So there is a limit on how much conventional grid following inverter-based resources can be accommodated because of system strength concerns and also on a wider grid size level because of frequency stability concerns. System operators to address this may limit output from inverter-based resources and supply remaining load with synchronous generation to ensure that there is sufficient system strength and inertia being provided. And this is, as I mentioned in my previous presentations, what's being done, for example, in Australia, same as in Ireland and Texas. It's implemented in different ways, how it's enforced, but overall goal is the same. And so such operational constraints in the long run, they will impact output from inverter-based resources and may impede further development of these resources, making them uneconomic. What can be alternatively done, synchronous condensers can be installed to provide grid support, but there are associated stability constraints if not thought about ahead of time. And also, as I mentioned, grid reinforcement, which at times can be expensive and time-consuming to implement. Also, some improvements can be achieved with control tuning. Next slide, please. So where it all started, we actually had a real-life case in about 2012 timeframe where we had a wind farm connected at 69 kV line and was connected to the rest of the grid through 2 parallel 69 kV lines. And so at some point when one of the lines was on plant maintenance, this wind farm became radially connected to the rest of the grid, which further increased impedance between the wind farm and the grid and electrical distance, as I mentioned. And so that resulted in negatively damped voltage oscillations at the interconnection point. So what you can see at the top graph here is a PMU measurement from that site, as well as on the bottom graph, this is what was replicated in the simulation once this happened and the wind turbine wind farm tripped. Then we've done some investigation, done simulations to replicate it. It required some back and forth with the model vendor because initially we couldn't see this response in the simulation. So what lessons learned from there is that we need to pay more attention to model and tool adequacy. There is impact from IBR controls when system becomes weak. And they can be control instability, control interactions, as Jason mentioned, and the mitigation options could be through inverter-based resource dispatch. So, for example, this problem here could be mitigated by just reducing, curtailing power output from this wind farm. Some improvement can be achieved through control tuning and systems reinforcements. Next slide, please. So in 2014, upon Handel study, we recognized limitations of single plant short circuit ratio characterizing system strengths. So as I mentioned, initially we just used short circuit ratio at a given node to try to figure out if there are indications of weak grid conditions or not. But then we realized that in an area such as Panhandle area, we need to look at nearby inverter-based resources as well. And single short circuit ratio ignores impact from other inverter-based resources. And so at times, if you look just a single short circuit ratio, it can give you an overly optimistic estimation of system strength. And so with that, ERCOT proposed so-called weighted short circuit ratio that recognizes interactions with other inverter-based resources. But the assumption is that all inverter-based resources are, you're just assuming they're connected to the same bus. And so you calculate weighted short circuit ratio as sum of short circuit power at each node in this area times power of inverter-based resources in this area divided by sum of power of inverter-based resources in this area squared. So it's weighted by power of each inverter-based resource. And weighted short circuit ratio of 1.5 were proposed as a minimum pre-contingency system strengths in Panhandle area based on results of PSCC study. Yes.
You have 13 minutes left, Julia.
Awesome. I try to be in time. One thing I wanted to mention that in this calculation, we actually consider actual power production of inverter-based resources. So it's not, P is not installed capacity, but actual production at the time, because that's what matters. Next slide, please. So this is just showing an example of calculation. I put it here. If you want to go through it in your time, we can go to the next slide. So we reevaluated Panhandle area in both phasor domain stability studies, so PSCC type of studies, as well as detailed electromagnetic transient studies, EMT studies that we do in PSCAD in 2016, 18, and 19, and now onward every year, basically. And weighted short circuit ratio of 1.5 was still found appropriate. So basically what we do is actual study, but then we see if this high level indicator of 1.5 short circuit ratio is still indicative of system strengths above this level. We found this concept applicable in the absence of local load and synchronous generation in the area, as well as considering electrically close inverter-based resources that are remotely connected to the main grid. We want to point out that weighted short circuit ratio is highly system dependent, even applicability of this metric, and it should be verified regularly through detailed studies such as EMT studies as the system evolves. So one of the examples I wanted to mention is relatively recently Lubbock power and light system interconnected into ERCOT area. So this is about 470 megawatt of load and 120 megawatt of synchronous generation, and this is located in nearby Panhandle area. And so with interconnection of this part of the grid, we found that weighted short circuit ratio concept cannot be easily used anymore. So you don't have this 1.5 metric that's readily applicable for all system conditions. And so even though this area also helped to improve weak system strength concerns in the area, but on the other hand, because it brings load and synchronous generation in the area, applicability of this metric becomes blurred. Next slide, please. So for the past 6 years before Lubbock Power Light interconnected into our system, we used weighted short circuit ratio, maintaining it in real time, and we monitor and calculate in real time and use it as an indicator of how much export can be made from Panhandle area. The calculation is built into a steady state voltage stability assessment tool that we also use to calculate export limit from Panhandle. And we recalculate it every 10 minutes based on actual production conditions and grid topology. And then so these two calculations, the voltage stability assessment and short circuit ratio assessment, determines how much output from Panhandle we can handle for the rest of the system. Next slide, please. So this is just showing how this transmission limit on the panhandle interface is being calculated, and it's varying in real time. Next slide, please. So as I mentioned, 2 synchronous condensers were installed in 2018 to improve system strengths in Texas Panhandle. So there are 2 175 megavar condensers. They were placed in locations where they could increase weighted short circuit ratio, but also they were optimized to provide voltage support and transient response. So location was chosen not only on short circuit ratio considerations. The design that we went for was to have high availability and reduce maintenance, because its impact on export out of Panhandle is very big and has economic impacts on plants in this area. Next slide, please. So you can see here, after installation of those 2 synchronous condensers, the transmission limit on Panhandle interface was substantially increased. And that's what you can see in the blue trace here. Next slide, please. But what also happened in 2019 Panhandle dynamic studies, we identified oscillatory behavior between synchronous condenser and the rest of synchronous generation in central and eastern part of Texas. So what you can see here is power oscillations where inter-area power oscillations where synchronous condenser is the main participant. And so we're looking into this. There is a way to control this through reduction of power output from Panhandle area, but one of the improvements that can be provided if inverter-based resources in the area are providing power oscillation damping, and that's something we're also looking into. Next slide, please. This Panhandle is just one of the areas we're seeing much of inverter-based resource growth coming in West and South Texas, contributing to stability constraints due to long-distance power transfer. These stability constraints can limit power transfer below physical limits, thermal ratings of existing transmission lines. We use generic transmission constraints as a tool to manage stability limitations. So generic transmission constraints is something that applied on one line or a number of lines as a transmission corridor to manage stability constraints in operations and in market systems. We've seen an increase in the stability constraints in recent years. That's what you can see on the upper plot. So this is the number of constraints that we're seeing implementing every year. And we need better tools in real time to calculate limits, because currently the limits on those stability constraints are based on offline studies. You can go to the next slide, please. So this is just showing a number of tools that we are using in planning and in real time as we're seeing more inverter-based resource penetration. So as I mentioned, we're regularly using EMT studies in parts of the grid, primarily Panhandle, near Panhandle area in South Texas. We have this weighted short circuit ratio calculation. We use PSSC for transient stability analysis, and also VSAT tool for steady state voltage stability analysis. We use again weighted short circuit ratio tool in operations, offline tables to determine limits on generic transmission constraints. We're also working on online transient stability assessment tool, because we recognize that offline tables may introduce some inefficiency at times, but may also be overly optimistic because they are only geared to studied system conditions, and it's better if we consider real-time conditions during transient stability assessment. And so currently in implementation is TSAT tool in real time. And we do online voltage stability assessment every 10 minutes. And so this is where model accuracy and usability becomes really important, and there are a lot of efforts going on in ERCOT to improve accuracy and verification of dynamic models. Next slide, please.
Well, you've got 5 more minutes.
Right. Good. So just a little bit about, I mentioned we started doing PSCAD studies, EMT studies in PSCAD. And this is to assess instability they may not be identified in BSSC and confirm adequacy of dynamic models in the simulation tool, and also to identify, we previously used it to identify if weighted short circuit ratio of certain value is still applicable or not. But PSCAD tools are complicated and time-consuming, and they require a lot of understanding from engineers. Andrew Isaacs had a really good talk yesterday in NERCIRE PWG meeting, talking just about that. And so this is just an example from a recent 2020 Panhandle PSCAD study showing that for area that is about 500 buses, had 60 PSCAD models to represent this 10 gigawatts of inverter-based resources in Panhandle, nearby Panhandle. And it takes about 2.5 hours to simulate just one contingency, even though we use parallel processing to speed up calculation. And this area, as inverter-based resources, are being added right outside generic transmission constraints to avoid curtailment. These areas are basically just increasing in size, and PSCAD models are becoming larger and larger. Next slide, please. I just wanted to say a few words, because I'm talking about weak grid, and you may ask, where single interconnection, we should also be concerned about frequency and inertia and all that. So we started looking at inertia and if it's a concern. Starting from 2013, we set up inertia monitoring, initially offline, and then in 2015 it was added to the control room. So what you're seeing here is each box plot is representing distribution of inertia based on hourly real-time data. And the lowest points basically showing you minimum inertia in every year. And what you're seeing in the green dotted line on the top is gigawatts of wind generation that we had installed by the end of each year. So you can see as wind generation on our grid was growing, inertia was actually not increasing at the same, decreasing at the same pace. And there is a number of factors playing in here. And this is because our load is growing. So we still have a lot of, our consumption is still growing, and there is a lot of use for synchronous generation on our grid still. We also had, as I mentioned, coal units retirements, and at the same time, a number of large combined cycles were built. And combined cycles with the same size, they have up to 1.5 times higher inertia contribution. So you can see in some years, even 2015, 2016 timeframe, inertia actually increased as amount of inverter-based resources was increasing as well. And so you can see it remained pretty steady. One outlier was March this year, where we hit 109 gigawatt seconds of inertia, and we think that maybe it's not as influenced by number of inverter-based resources on the grid as much as consequences of February event, where some synchronous generation was on maintenance after the event, and so less of it was available and inertia went down. So we'll keep monitoring this trend and see what happens next spring, because inertia kind of goes low in spring and fall nighttime when wind is high and load is low. Next slide, please. So we implemented a number of measures just to make sure that we have situational awareness about inertia, and we have sufficient amount of frequency containment reserves. When I'm saying frequency containment, these are reserves that are used to arrest and stabilize system frequency. We determined critical inertia level as a minimum level of system inertia that we need to ensure that frequency containment reserve has enough time to respond to frequency events and avoid under-frequency load shed. We monitor inertia in real time. If inertia is close to critical level, system operators have processes in place to start additional synchronous generation right now. So that's the workaround that we have, but we never actually got to that critical level of inertia. So that's just a precaution for now that we have. And above critical inertia, we base requirement for frequency containment reserves based on inertia conditions. So we need less reserve when inertia is high and more reserve when inertia is low. We recently introduced fast frequency response because we find it's more effective to arrest frequency when inertia is low. And so that allows us also, once the service is fully subscribed, to go down in critical inertia level. Next slide, please. And I'm about to conclude. So just to conclude, there are increasing stability and system strength challenges with more inverter-based resources connected on the grid. It's complex and time-consuming to model and simulate. There are additional stability challenges, as Jason as well mentioned. It may require tight voltage control, identification and management of stability constraints in planning and operations becomes challenging. We need early communication with developers to make sure that we have adequate model, and we are continuing to explore ways to reliably operate the grid with high inverter-based resource on the system. And then diminishing inertia and faster rate of change frequency, we haven't found it to be a concern yet, but we kind of prepared ourselves ahead of time and addressed it with situational awareness and faster frequency response. With that, thank you for attention. I'll be ready for your questions.
Julia, thank you so much. ERCOT's really on the cutting edge of what's happening with high penetrations of inverters, and we're really grateful to be able to learn from what you're doing there. Travis, do you think we have time for one question? There's a lot of questions for Julia.
Great. Feel free, Debbie. Go ahead there.
Real quick, I'll just ask one and maybe we can get to the others later. But someone from the Alberta ISO asks, what transmission topologies does ERCOT consider for assessing short circuit levels in connection and planning studies? Do you do N-0, N-1, N-1, -1?
I'm not sure from the top of my head, so I will get back in the end with that. I just don't want to make it up.
Okay. Okay. And we have the opportunity later to provide written answers to questions. So please don't feel like your questions will go unanswered. We can prepare a written answer and get back to you later. But thank you again, Julia, for that presentation.
Yeah, great. That was Dr. Julia Matamosian of ERCOT. She's a lead planning engineer there. Thank you so much for taking us through that last hour there, Julia. Next up, we're going to turn it to Nick Miller. He's principal at Hickory Ledge. He'll be discussing export stabilities. The export stability study comparing grid following inverter-based resources, grid forming inverter-based resources, and synchronous machines. Nick, I'll turn it over to you.
All right. Thanks, Travis. Next slide, please. It's great to be here and great to follow Julia, who's always got such up-to-date insights and things. I still want her to use that picture of me standing next to the battery at Metlakatla 27 years ago when I was a little less gray. But little context to build on Julia's narrative and why you in the audience need to be at least at some level cognizant and concerned about the stability issues. So this is a resource map which I failed to give credit to, but it comes from the national labs that I've annotated to show something that you all know, which is that we as a country have wind and solar, so IBR rich resources in places that are relatively far from the population centers where they're going to be, where the power is going to be used. And the scale of the problem is huge. You've seen Julia's real life experience and you're starting to feel it. Those of you that are on the call from MISO, for example, are looking at getting wind out of those high plains down towards the resource centers. Those of you in WECC are trying to get solar out of the desert Southwest and wind out of the Northeast part of the West. So this stability question, is more than just for the nerds. This is, we as an industry have to use not only the transmission we've got, but any new transmission we build to get these resources to where they're consumed with the utmost efficiency. Well, this isn't just an interesting question. This is a pivotal question to our success. So that's just a little sales pitch. You might find some of the details of stability tiresome, but the system doesn't work if it ain't stable. So next slide, please. So having said that, I'm going to, for some of you, maybe be a little tedious. We're going to go back to some real basics so that we can delve into what it is that drives these stability questions at a somewhat more fundamental level. So we have a little sketch up at the top left, which is the cartoon version of this export problem, where the left side of the little sketch is where the wind or solar resources are, and the right side of the sketch is where the system is stiff and there's some impedance in between. So the system doesn't get any simpler than this, and I'm going to be talking from that for about the next 15 minutes. So you might roll your eyes, but there's a lot to be learned. The figures below are from stability runs, and those of you that have been listening to me for years have seen me use this figure for getting close to 20 years. These are this is a stability case, that is positive sequence fundamental frequencies, or PSLF runs, could have been PSSE, for a wind plant on the WECC system over in eastern Colorado. So the black lines on this are classic fault and clear stability from a 162 megawatt wind plant, pushing power towards Denver in the WECC model. And the red traces are all of the things being identically equal with a synchronous machine of similar rating. So both these were GE equipment. This is work done while I was at GE many years ago. And the red traces will be very familiar to those of you that live in the stability world. There's a fault depression, you clear the fault, the machine swings around. If it is positively damped and comes back to its stable operating condition, and the voltage swing during recovery is not too bad, you have a success, otherwise it's a fail. The black is always a surprise to people that haven't worked with inverter-based resources, and it's rather better mannered. So I'm going to spend the next few minutes delving into what's going on with this trace. On the right-hand side is also a stability case that those of you that work in this world will recognize, and that is for a long fault depression, synchronous machines lose synchronism. So this is for a very long, nasty fault. The red trace, the fault's cleared, and the machine snaps off, slips a pole, trips. You've all seen that. You expect that. That's why we don't have real long fault clearing times. But it is of some interest to note that a very long disturbance for an inverter-based wind plant is not such a big deal. That can be important, and we'll return to that later. So next slide, please. So on the left, we have the same trace, the stable case, and on the right are really basic tools that many of you know, maybe all of you know, and we're going to just look at it through the filter of fundamentals with this trace. So the left pair for red up top is the synchronous machine. The green with the black numbers is for the inverter-based generation. These are grid following inverters here, but that's not terribly important to this discussion just yet. And the number one is this pre-disturbance. So we have power angle curves left. We're going to use equal area criteria. You'll remember that. In the middle, we have power transfer nose curves. And the system is stressed, so it's somewhat out on the nose, but back from the end of the nose, because that's unstable. And then on the right, we have the phasor diagram where there's a system separation associated with pushing the power from the resources to the receiving system. Really basic stuff. So next slide. At time 2, we have a disturbance somewhere along that route of egress. Okay, so this is every planning engineer's sort of basic scenario. The voltage drops back at the sending end. Bars are sucked out of the resource. The synchronous machine loses its ability to push power out, as does the inverter-based machine. The synchronous machine now has no place to put the watts, that are coming into the drivetrain. So everybody's going to recognize that. We're down on a collapsed nose curve because of the presence of the fault in the middle, and the phasor diagram at the sending end has collapsed to 0.2. Very familiar, everybody. Next slide. So at time 3, okay, the fault has been on for a while. The voltage has further collapsed. It collapsed more deeply for the inverter-based resource than it did for the synchronous machine, because the inverter-based resource delivers less fault current. There were several questions about protection and other things. We're not going to address the protection question here, but the fact that there's less current delivered means that the voltage is depressed more deeply, and we are collapsing that during fault nose curve. So there's even less power getting pulled out during the disturbance. So very similar between the two resources during this fault. And then next slide. So we clear the fault. The voltage pops back. The synchronous machine immediately, because the angle has pulled out, tries to push extra megawatts out into the system, and it's highly stressed by doing that. So you see 0.4 on the nose curve doesn't make it back up onto the pre-disturbance nose curve, which means that the ability to get the power out is compromised by low voltage along, including back at the sending end. In comparison, the inverter-based resource didn't swing out as much. So the angle is very different at 0.4 for the inverter-based resource than it is for the synchronous machine. So everybody, this is one of the things that inertia does for or to you. The synchronous machine has inertia. In this case, the inertia of the synchronous machine is not necessarily doing you a favor, because the machine has accelerated and it is now pulled out, and it must get rid of its extra megawatts during the resynchronization as it moves up the power angle curve, or it will slip a pole. So that's all basic power system stability stuff that you're familiar with. But the point is that the wind turbine or the PV plant doesn't have a direct speed coupling to the system. So even though the blades of the wind turbine in this case accelerated during the disturbance, the inverter doesn't need to push the megawatts out as vigorously. That allows the voltage to recover better. You see the little dip, so we'll go to the next slide. Next slide, please. There we go, fine. All right, so into the disturbance just a little further, we reach the top of the power swing for the synchronous machine. You see the equal area shaded in orange are equal. That's basic theory. That means that the system has dissipated the accelerating energy that it acquired during the fall, and it's going to go back, and it's moved. It hasn't actually quite gotten up onto the old nose curve yet because the voltage hasn't recovered. If I looked very carefully at the red voltage trace, you would see that that was a marginal voltage recovery by WECC criteria, right? Remember that post-fault voltage swing, post-clearing voltage swing can't go below 75% for a class A and B type disturbance in WECC. So the system has taken this big angular swing. The excitation systems and other things are trying to reestablish the voltage and pull us back up onto a healthy nose curve without going past the end. Whereas the inverter-based resource still is constrained by the nose curve and the requirement to reestablish the voltage, but it is not constrained by the accelerating energy of the wind turbine. All right, so what did all those words mean? It means a bunch of important things for export stability. First, we aren't constrained by the accelerating energy during the disturbance. We could do other things. B, these network equations that give you the power angle curve and the PV nose curve are not dependent on the resource. Those are network quantities. And you cannot go to a post-disturbance condition that violates the power angle curve and the PV curve, no matter what the resource is. So there is an entitlement given that is associated with the network topology and not with the resource. So all the rest of that is details. If you've got a place to go that will be acceptable, if 0.5 exists and it is an acceptable condition, then the question is, are the controls sufficiently robust to not fail on the way to that? That's what the stability question is about. Okay, so next slide. So I'm going to go through this quickly because Julia really did a great job of talking about effective short circuit ratio, but it is a little bit important because we as an industry, we're still struggling a little bit. So all these words here say more or less what Julia said, which is as the system gets weaker, as X gets bigger, the stability problem gets trickier. And this topology that's in this little drawing isn't sufficient to give you the whole story. So she said that very well. But let's go on to the next slide and just look a little bit at the differentiation. Yeah, Debbie.
13 minutes.
Okay, I'll be there. I wouldn't dream of going over, right? So on the left top of this figure is the condition that we're experimenting with, where all of the power is being pushed from some remote place to a load center. You can't get wrapped around the axle of thinking that that is equivalent to the problem on the right, where the power being generated is being consumed more or less electrically where it's generated, and the system, the rest of the system is someplace remote. That's the Hawaii problem, all right, where X is going to infinity. That's a good application for grid forming, but it's not the export problem. So there's a bunch of other words there that come into play on this slide, but fundamentally don't convolve the problem of getting power out of a remote place to a massive grid like we have in the West, like we have in the Eastern interconnection, with a situation where the entire system is dominated by the left-hand side of the figure. So let's go on to the next slide. Okay, so we're focused on the top left. I forgot about that transition. This is from a study that we published several years ago. Again, while I was still at GE, this is work funded by Admiral. This is some study of the Western interconnection and some future with a lot of wind and quite a bit of the synchronous generation offline. And it shows very similar results to the one that Julia showed earlier, so I won't say too much about it. The system there's 3 traces on here where the system is getting progressively more stressed, which is more wind power, less synchronous machines. But the thing I want you to learn from this thing is that the warning signs that we are accustomed to looking to, that are all over WECC criteria and NERC criteria to look at what that recovery looks like, aren't terribly useful for this particular exercise. You see the green and the blue traces didn't show a substantial post-fault voltage dip that we're used to looking for. The system went from pretty sleepy green and blue cases were really quite stable to a fail during the fault, which is one of the things that Julia showed. So that's the bad news. The good news is that this problem was mitigated by controls that were designed for weak grids. And the simple version of that is, don't ever try to push watts, megawatts, into a system with a sick voltage. So you always have to fix, for the export problem, rule 1, fix the voltage. Rule 2, then push the power out. That's Dick's rules of export stability, and it's good ones to live by. So next slide. So we have a bunch of tools. I think people on the call are familiar with that, and you've heard some of these things. We have better controls. The industry has gotten spectacularly better with inverter grid following inverters that tolerate progressively weaker systems. So Inverters that are designed for stiff systems don't work well in weak systems, so don't make that planning mistake. All models aren't the same, all inverter grid following inverters aren't the same, but you cannot exceed the entitlement. You can't violate the things that essentially come with Kirchhoff's laws. You can fix the issues by adding more transmission. You can stiffen the system with synchronous condensers. That last case was mitigated by turning a couple of the old, possibly to be retired coal plants in the Western interconnection into synchronous condensers, similar to the experience that Julia showed of adding condensers. And then there's other things we can do to stiffen the grid up. Next slide. So I'm going to finish with a quick view of some recent work we've done. I give my credit to my colleague Matt Richwine, and we just postulate that there are aspects of the stability. I just showed you a whole bunch of things where the grid following inverters get better performance than synchronous machines, but there's other aspects of synchronous machines that are superior, as you've already been exposed. So the question is, can you get the best of both worlds with grid forming inverters? So next slide. So we set up a detailed PSCAD. So these are, and we go between grid following, GFL, grid forming, GFM, and synchronous machines, all other things being equal, and a very detailed representation of the equipment with commercial vendor-based OEM controls, but a single snapshot of them, and play games with the power transfer, the length of the AC lines, and what to do at the midpoint. So thousands of cases on a very simple system to try to tease out some basic insights. So next slide. And sorry that this is an eye chart, but there's a whole bunch of cool things to be learned on this, but also a bunch of caution. So what you've got here is one snapshot from the analysis from the thousands of cases that we did, showing vertically left to right stacks of a relatively weak grid, right? A few years ago, we would have called a short circuit ratio 2.2 very, very weak, not so much anymore. Marginal, Julia's marginal metric was 1.5, these are 1.4, and a short circuit ratio of 1.1, which is very weak. The rows are grid forming, synchronous generator, GFM, and insofar as we were able, all the things are equal. And the coloration is acceptable, marginal, and fail. So you see the grid forming in this case, and I can't say that enough times or loud enough, in this case, with this set of assumptions, shows superior performance. But you see the green arrows in there. The question that we as an industry have not resolved, and Sebastian's going to have a lot to say about that, is how much of that is control, and is there something intrinsic in grid following versus grid forming that gives you superior export stability? I want to drive that home. This is export stability. This isn't all aspects of stability, but export stability is the elephant in the room for the next few years for the industry. So this is very encouraging, but there is a question in all of our minds as to how much of that is control and is any of it intrinsic. So next slide. So we generated some maps left to right on each of these three cells is longer fault duration. Y-axis is grid stiffness, and the colors are acceptable, marginal, and unstable. Couple things to learn from this exercise. One is that the duration of the disturbance, so for inverter-based resources, isn't very important. We seem to see that repeatedly. That isn't a widely accepted consensus. Deepak might have a few words to say about it. You know that longer disturbances are worse for synchronous machines, right? We do critical clearing time. You worry about, right, how far back are you from the stability limit? Well, critical clearing time may not tell you what you want to know. The other thing is you got to be really careful the basis on which you do the short circuit calculation, and I will leave it at that with that slide. Next.
You got 4 minutes left, Nick.
All right. So just a couple of closure points. We see this is the voltage swing and the active power swings of a condenser put at the middle. And this was, Julia already talked, and they have observed stability issues. They've observed stability issues with synchronous condensers in Australia. And what we saw here is you get swings in voltage and power. And the main thing I want you to take away from this slide is that you have to be careful when you see your system oscillating at frequencies that you're accustomed to fixing with power system stabilizers. The guts of the swings can be driven differently, and things like power system stabilizers may or may not fix the problem. So in this case, the dynamic interaction between the grid following inverters and the synchronous condensers were very complicated. There were two swing modes that interacted with each other. This is a fail. The swing is too violent, although it is positively damped. If we look at the next slide, please. This is a similar condition. We see the condenser still swinging around, rather poorly damped at the bottom, but with minimal interaction with this version of the grid forming converter. So we were pretty excited about that, but it's still not clear whether that's just control or whether there's something intrinsic. So next slide. So in summary of the findings of this little exercise that I just showed you, we saw that particular rendition of the grid following inverters had similar stability limits around normal disturbances to the synchronous machines. We found that this particular grid forming inverter was noticeably better with more benign swings and was tolerant of a weaker system. We found that the locations for faults were very sensitive when we're talking synchronous machines, but less so for inverter-based resources. Similarly, less dependence on the time. And then there's a bunch of observations about location, et cetera. What you want to take away from this as practitioners is that some of the things you're accustomed to looking for in your stability work aren't necessarily good markers of a system that's in distress or that's near the edge. So we have some learning to do. In general, we see good stability results with grid following, with present technology grid following wind and solar. Generally better than synchronous machines, but the warnings and the practice haven't quite caught up, and the tools have not quite caught up to help you understand how close you are to using up the entitlement of the transmission system. So this entitlement question is really a burning one that we don't have fully resolved. Last slide, please. So just to kind of recap, this is maybe a little bit the truth according to Nick, so you can take it with a little bit of sodium chloride, right? When we're talking about going to very high levels of inverter, you heard this from Debbie and everybody else, are you ever there? Not always. So don't worry, don't think we're a long ways from 100% or very high inverters because your annual percentages are relatively low. Furthermore, there's pockets, and you just heard that from Julie and just heard it from me, and you're finding it in your studies. There are areas that are 100 that will now or in the near future be 100% inverters, trying to push that zero carbon power out to the load centers. We aren't to a give me Article 1 of grid forming inverters. All right, the art is not fully cooked. BESS is there for the most part. One might argue that I'm being a little pessimistic. I am of the school that joining Julia and many others that say we shouldn't be building any more utility scale BESS in this country that doesn't have grid forming. It is not clear that we are there or need to be there for wind and solar yet. but we do need to get moving forward. We do not want to just mimic synchronous machines. Inertia is not always your friend. Right? We can and must do better. And finally, don't panic. There's every reason to think that we're going to have this next round of challenges well handled. And the reality is the industry has made spectacular progress in making grid following inverter-based resources behave very, very well, and frankly, better than synchronous machines in many regards. Okay, I left a minute, Debbie.
Thank you so much, Nick. That was a great presentation. I should add that the last piece that Nick presented on the export stability work with Pellus Energy, there's an hour-long video on that. I'll post maybe some of this in the chat. Yeah, there's also an hour-long video of Julia's work with the scan of grid-forming inverters across the world. And I'll put some of those in the chat if people are interested in diving deeper into these topics. So Nick, there's, so I didn't see a whole lot of clarification questions. So I'm gonna ask some of these top ranked questions that are on the Slido. Is a grid forming inverter capable of working alone at a short circuit ratio of 0 or only at low short circuit ratios?
Yeah, so the short answer is yes. The long answer is it depends on the grid forming inverter a little bit, but you know, and again, maybe because I'm old and cranky, but the 1995 Metlakatla battery energy storage system, so it's been in operation for 27 years, is grid forming. It is used to black start that grid. They start all the other machines in the system against the battery. It sets frequency, it sets voltage, and it provides enough current for all the protection in that microgrid to work. And it's been in commercial operation for 27 years. All this stuff isn't brand new.
All right, thanks so much, Nick. And Travis, I think we're doing a break now.
Yeah, let's go to break right now. Again, that is Nicholas Miller with Hickory Ledge. Nick, thanks so much for joining us, and he will be on at the end of the workshop to answer any more questions. We see a lot of them coming into the Slido. So let's go ahead and take a break, and we will come back in 5 minutes. Sounds great. We'll see you guys here in 5 minutes. Thanks so much. Head up to go. We're seeing your presenter mode and your laser pointer as well.
Awesome.
We'll give people another. All right, it looks like it's been about 5 minutes here. We'll get back to it here. Thank you again for joining us for WECC's grid forming inverter-based resource discussion this morning and into the afternoon. We're going to be talking about modeling of grid forming inverter-based resources and frequency response in a 100% IBR grid. We've got Dr. Deepak Ramasubramanian on the line, and you can, excuse me, take it away.
Thanks, Travis. So after those great presentations from Jason, Julia, and Nick, we'll shift gears a little bit and talk about modeling of grid forming resources and generally frequency response in a 100% IBR system. And the aspect of modeling, we'll keep shifting a little bit between EMT modeling and positive sequence modeling. We'll see how you could leverage software like PSLF and PSSE to represent grid forming inverters, and also spend some time looking at frequency response and the nuances that come about with frequency response. There were questions in the chat on rate of change of frequency, emulated inertia, and so on. So we'll talk a little bit about that as we progress through these slides. But before we go there, I'd like to put this set of slides just talking about models in general. We hear a lot about inverter models. We hear a lot about different simulation domains and environments in a lot of the presentations that we come across in industry. And just like to keep things a little bit in perspective when we talk about some of these models, especially to keep in mind that a generic model does not always imply that the model is a bad model. Or a model from a manufacturer, a user-defined UDM model, as you may have heard from a manufacturer, doesn't always imply it's a good model. A positive sequence model, which you might see in software like PSSE or PSLF, again, doesn't always imply a bad model for an inverter-based resource. And on the flip side, an EMT model, a PSCAD or an EMTP or a Simulink kind of a model doesn't always imply a good model. So keeping these things in perspective, we have to understand that pretty much all models have limitations, and one needs to really identify whether the appropriate type of model is being used for the study that is to be done. Is the model being used in a correct manner? Are all the appropriate and relevant control loops represented for the study that you want to carry out? Very important, is the model appropriately parameterized? You can have the most detailed model you want, and if the parameters are not good, if the parameters are not site-specific, if they are not really representing the equipment, then that model is not a good model at all. And on the other side, you could have a simplistic model, but if the parameters are chosen in a good manner, then you could actually have a good response or a useful model. And the last point is any model needs to be validated. So are there sufficient validation results available to represent that model behavior and to show that that model is good enough for the study that is to be done? So if we keep this in perspective now, where we go in with a little bit of an open mind regarding models, saying that the models can really span different domains and they can span different kinds of simulation environments, then now using that, let's take a deep dive into modeling grid forming inverters. So again, regarding grid following, grid forming, what you may have heard at a very high level is things like delivering a specific amount of power in a grid following versus setting up voltage and frequency, being able to operate with a stiff grid versus not being able to, or not necessarily requiring a stiff grid to operate, and from control loop elements, aspects about compulsorily having a phase lock loop versus compulsorily not having a phase lock loop. Now, this kind of a distinction between grid following and grid forming is, we acknowledge that it's a very high level distinction and that there is more nuances involved here with respect to what we can really call grid forming versus grid following. But these are the kind of definitions or the distinctions that have been put forth across very different kinds of industry environments and forums. And as a result of that, one may have heard things like a grid following IBR is a current source. It has a phase lock loop or a PLL. A network with only current sources and PLLs cannot be stable, and hence one transitions to grid forming. But it's a little bit advantageous and it provides more perspective if we step back a little bit from this kind of a notion or a notation and really think about it from basic circuit theory perspective. And when you do that, one recognizes that as we go towards 100% inverters, and even in a 100% inverter-based system, Kirchhoff's law doesn't automatically vanish. You still have Kirchhoff's law, you still have Ohm's law. Everything that we learned in Circuit Theory 101 in undergraduate school still applies, that those rules and laws, they still hold forth, and they really control how our currents and, and voltages flow across the network. So if you do have a system which does have only current sources, then yes, definitely the voltage levels in the network are decided by the current and the impedance in the network. So if you have a certain amount of current which is coming out from the current source and you have a certain amount of impedance, the voltage level in the network is determined by that. But at the same time, if you have a change in the network, say something like a load increase, where you change the topology of the network, you change the properties of the network, and if you do nothing to change the current being injected into the network from the variety of sources, then there is a possibility that the network can collapse. That is primarily because of the fact that you have much more impedance in the network, you don't have enough current being injected, and your voltage can collapse as a result. But what happens is if you do change the way in which this current is injected into the network, if you do provide an appropriate value of current injection, then we know from basic circuit theory that this network can have a viable solution. You can solve Kirchhoff's current law and Kirchhoff's voltage law in a current source network and obtain a viable solution for voltage. So the key here is that the values of these injected current, they have to be controlled in a timely manner, and that is critical. It's how you inject current into this network, and can you control its injection in a timely manner? That's what decides whether this network will continue to remain stable or not. And if you do this in a very robust way, if you decide or if you set up the controls in a robust way, you can have an all 100% current source network really operate in a stable manner, wherein for an increase in load, here you have a 10% increase in load, you can actually get a fantastic frequency response, and you can get sharing of power across the different current sources. So what does all this have to do with grid forming? What does this have to do with modeling? The importance it has with respect to modeling and grid forming is it now opens up ways in which we can derive grid forming models utilizing our existing simulation tools that we have handy, and we can then leverage that to maybe get 80% of the way. And we can then also look at grid forming behavior from a system planner perspective rather than looking at individual control elements. We've seen, or we saw on the previous slide, that it's possible for a continued operation of 100% current source network, and we intentionally stay away from black start and system restoration at this point in time because it's a special operation scenario even today. Not every synchronous machine plant can do black start or is black start capable. A synchronous machine plant also, to be black start capable, requires a special operating condition. So if we split our operation domain of inverter-based resource systems into continued operation on one side and system black start on another side, continued operation is what we're talking about today. System black start is a topic for another day, which we can go into much more detail and apply some of the same principles that we speak about today, but in a special operating mode. As Nick mentioned, that inverter-based resources that have been designed and tuned to operate in a strong grid can have issues in weak grids because the nature with which they have been tuned, the design rules that have been applied to them were from the perspective of a strong grid, which means that if a weak grid manifests, they could have issues. And in that aspect, a phase lock loop is just one part of the entire control architecture in order to obtain synchronization. It's not the main or the sole cause of instability. There are other control loops that react and play a role in causing instability. Yes, the phase lock loop plays a role, and one can determine instability by looking at the phase lock loop and its performance, but at the same time, that can be tuned and it can be made more robust and it can be designed to operate in a weak grid environment, which means that inverter controls with phase lock loops can also be developed for 100% inverter systems, provided we tell the inverter-based resource what kind of services it needs to provide and in what time it should provide that service. And once it does that, it's all about providing the services for the system, and we can then get a stable operation. And in this regard, we can then now flip and turn the definition of grid forming inverter to use a performance-based approach, wherein we specify that this grid forming source is defined purely based upon its capability and the grid services it provides, which can be operating with and without synchronous machines, operating with other inverters, providing positive contribution to load imbalance, voltage imbalance, fault write-through, while meeting its equipment limits and while meeting standard acceptable metrics. So we might have under-frequency load shed as a metric which need not be crossed, right? We don't want to reach that under-frequency load shed threshold. So as long as we meet these acceptable metrics, or maybe like the WECC transient voltage recovery criteria, as long as we meet such metrics, then a grid forming inverter or a future inverter can be defined pretty much from its performance and the services that it's required to provide. And then you can have a subset of these resources that are also designated as black start resources. And if we do this, or if we characterize this performance purely from the services criteria or services perspective, then the actual control loop which is used inside the inverter can become something which is not necessarily to look into in more detail from a system planner perspective. It will be details that an individual equipment manufacturer needs to pay attention to, because they need to ensure that their control loops are well designed to provide the services that is required. And in fact, here's an example. We just took 4 different kinds of control implementations of grid forming behavior, wherein you have phase lock loop based, group based, virtual synchronous machine based, and dispatchable virtual oscillator based, and tested it for some of the strict dynamic model acceptance test guidelines that AEMO has, wherein you have a pre-fault short circuit ratio of 3, a post-fault short circuit ratio of 1, a very large X by R ratio, maybe similar to Nix's infinity and beyond reference that he had. And then we have situations where you have a 3-phase fault with 0 impedance. And even though the models are not optimally tuned, you can see that, yes, there are slight differences in the performance, but overall, they're pretty much stable and they show the general trend of response, which means to show that the exact control method or the exact control element which is being used is not necessarily something we may need to pay attention to too much from a system planner perspective. It's very that I'm intentionally re-emphasizing the system planner point, because I don't want to give an impression that control loop design is not important. It is important for the inverter manufacturer and the person who's designing the inverter control loop. It need not be that important for a system planner or an operator who at the end of the day just wants services from these inverter-based resources and wants them to provide that in a robust manner. So how does all this link to positive sequence modeling, and where do we take this? So some of you may be aware that there are these suite of models called the positive sequence generic models, also known as WECC generic models, and they are split up in a modular fashion, wherein you have plant controller, you have an electrical control, and you have what's called the generator converter model. Predominantly for the past few years, we have been using this model called the REGC_A, which is a current source representation. And we've been working through the WECC model validation subcommittee to create these new suite of models, which has now been named as REGC_C, which has a voltage source interface. Now, what this REGC_C model is it is a much more robust model, especially for low short circuit regions. And we've shown that it can really provide a representation of oscillatory behavior that manifests in low short circuit environments. So here's an example study. The REGC model itself has representation of phase lock loops and inner current control loops and all the good things that are there inside an inverter. And it can be tuned to provide a much more accurate representation of the dynamics of these fast control loops in the inverter. And with that, you can see that here, when you compare it against an EMT domain black box model obtained from the manufacturer, the EMT domain model showed oscillatory behavior when the short circuit ratio went from 2.5 to 2. The REGC model is also able to show a representation of the oscillatory behavior, though not at the same peak-to-peak value, but it's sufficient for a system planner to know that, hey, something is going on in the system and we need to investigate this further, as compared to the existing REGC_A model that didn't show any oscillatory behavior at all. Interesting tidbit here is that the user-defined positive sequence model that we obtained from the OEM or the original equipment manufacturer for the same setup was unable to show the oscillations, which goes back to the initial slide that we said that let's not have any preconceived perceptions about models and their accuracy or whether they are good or bad, because the spectrum is just so wide and we need to have validation exercises performed. Now, this model that we speak about, the REGC, because it is specifically designed for low short circuit environments, and because it can provide this good picture in low short circuit environments, it can equally be tuned well to operate in a short circuit ratio of 0 or a grid forming representation. So as this example, you can see that when you compare a PSCAD grid forming behavior versus a representation in PSLF and PSSE, which is the positive sequence tools, you can see that there is a good representation of the trend of the response if you had a system islanding event occurred at time is equal to 5 seconds. There is a little bit of coordination between the plant controller and the electrical control in the EMT model that needs to be sorted out, but irrespective of that, there is a good representation of the trend of the response. But these models have to be parameterized with diligence and thoroughness so that they can represent the behavior that we are asking for. And if we take it to the next step, we can compare that across different flavors of grid forming implementations. We tried across virtual oscillator, group-based, PLL-based, and a few unknown implementations. This model holds its water, so to speak, that it can provide a representation of the trend of the response in positive sequence environment. And still more work is left to be done, of course, to complete the tuning and to make it more robust and maybe even have more improvements to this model over and beyond what we already have. But the fact that the results are encouraging and they provide this trend of response really goes to show that we can continue to get more benefit from new positive sequence models, which is not meant to say that they can replace EMT or you don't need to do EMT studies. What's meant to say is that it provides more tools to a planner so that they can get a more informed picture of their system and really identify where all they need to do EMT studies rather than having to do EMT studies on a whole set of contingencies, which may be computationally not very efficient. Now, there was a question which a member from a WECC utility asked us a few months back that, hey, we have these new positive sequence models and all of that is very good, but can we really study something like a system islanding scenario in a software like PSLF with these new models, wherein suppose there is an area or a zone of the system that needs to be isolated from the rest of the network for whatever reason, maybe a wildfire is coming through, maybe there's a tornado blowing across, for whatever reason, there needs to be a portion of the system that needs to be isolated from the rest of the network. And we want these two networks to continue to operate, but there is an islanding behavior that has occurred. And the portion that islands is only inverters and nothing more. Can we study such a behavior with this REGCC model? So we set up this example case study wherein, yeah,
10 minutes
thanks,
left.
Debbie. Yeah. So we set up this example study wherein we are using an IEEE test system just so that we can really make the results public. But you see that you have a system which has grid following inverters, it has synchronous condensers, it has one grid forming inverter down here, and it has a grid following inverter at the top here. And what we want to do is we want to island this portion of the network and then split it up with this portion of the network. So that the islanded portion has one grid forming inverter and one grid following, and the rest of the system has only grid following and synchronous condensers. And now we simulate this both in EMT domain and positive sequence domain. And this is what you see with respect to the frequency response, that the frequency in the main part of the system, this is the EMT result. Upon the islanding that occurred, the frequency increases because there's an overgeneration in that region. The frequency drops in the island with the grid forming inverter and it settles down. And you see a similar trend of response in positive sequence domain. It's not exact yet because there are still fine tuning in the system model that we need to do. But the fact is that this response is obtained and one can study these kind of things now in positive sequence is encouraging so that we can start using these models and start understanding what they can do for this kind of a system. But now here we come to frequency, right? Now you see that there is how do you assess frequency adequacy and how do you assess frequency response in this 100% system? How do we know that it will settle at this value of 59.85 Hertz roughly? And how do we really think about frequency response in this all inverter system? To address that point, let's think about it that IBRs, when you have them in the network, they can have reduced time to react to frequency imbalances because you may not have IBRs that are providing frequency response, like wind and solar. If they're operating at their maximum power point, they would not provide under frequency response, which means that there could be an increased chance of UFLS operation. There could be reduced inertial energy in the system from machines, which means that there could be a faster rate of change of frequency, and that could result to cascading environments. So to understand that, let's just take a very simplistic system of having this 3-machine 9-bus system, and you assume that there's sufficient spinning reserve available in all these resources. And if you have a 5% increase in load, then when you replace machines with inverter-based resources, you can see that if you have different types of inverter-based resource operation and different types of machine operation, like here you have machines with governors or machines with reduced inertia constant, and then having governors, you can see the impact of the reduction in the inertia constant of the machines. You can have inverters in constant power mode. You can have an increase in number of inverter-based resources, again with constant power mode, which means a grid following and they're not providing frequency response service to the system, just conventional primary frequency response service. And UFLS is triggered because ultimately at the end of the day now in this red curve, there is only one source which is remaining to provide frequency response. So the question we may ask is, the triggering of UFLS, is it because there are inverter-based resources in the system which have replaced machines, or is it because there are a reduced number of sources which are providing frequency response itself? And if we see that if you switch off governors in a synchronous machine system, you will start getting a similar response where UFLS is triggered, wherein the number of resources providing frequency response has reduced, which means that you can still have a chance of UFLS triggering. Yes, it is few seconds later, but the number of resources providing this frequency response really matters and plays a more crucial role than the way in which the frequency response is obtained from either synchronous machines or inverter-based resources. Because if you take the same setup, the same example, and you really make an inverter-based resource provide primary frequency response with governor-like capability, and even if you assume that there is 750 milliseconds time lag inside an IBR control so that it has time to really calculate frequency and then react to it, even with that, because by default, these IBRs do not have a mechanical time constant. There's no turbines involved. There are no governors involved. So there are no mechanical time constants involved, at least in solar and battery. Wind has mechanical time constants, but that's also something that can be dealt with. But let's assume here that you have solar and battery. Because there are no mechanical time constants involved, automatically the frequency response, the primary frequency response from an IBR is faster, which means that in an IBR without mechanical time constants, primary frequency response may be as good as fast frequency response for the same value of group coefficient and for the same value of deadband as compared to an synchronous machine system. And if you do have this, of course, you need to have robust inverter control, and you need to design the controls to be robust under varying system circumstances, but it's definitely possible and can be achieved. And in fact, FERC Order 842 asks for this kind of governor-like capability, of course, without the headroom and mandate to maintain headroom. That is a market operation perspective, which we don't want to get into here. But this kind of governor-like capability from inverter-based resources, providing natural primary frequency response, which is fast inherently, can actually make an inverter-based resource in a way grid forming. Because if you look at the frequency response behavior in the small time frame as soon as the disturbance occurs, and if we compare having all machines with governors, all synchronous machines with governors as the blue curve, synchronous machines with governors turned off, which is the orange curve, and then an inverter-based resource providing governor-type response, as soon as the disturbance occurs, the initial response that you see, the spike, that is not to be confused with inertial response from synchronous machines. That spike is a pure electromagnetic response that comes from a machine. The inertial response follows that. So the first spike is pure electromagnetic. The inertial response follows that. You start to see where the governor response becomes more dominant than the inertial response. And this kind of, in this time duration, definitely yes, that the inverter-based resource is more delayed in injecting its power. It's here, it's 500 milliseconds delayed because it's ensuring that it's calculating the frequency correctly. And it can cause an initial higher rate of change of frequency. But the moment it has understood and evaluated a good frequency evaluation, you can have much higher sustained energy injection from the inverter-based resource, which actually resulted in the higher value of nadir that you had from the inverter-based resource in the previous slide. And all of this we can...
2 more minutes.
Yeah, thanks, Debbie. And all of this we can relate back now to draft IEEE 2800 standards, wherein we talk about technically feasible capability and how fast it should be. And we can really see that if we do have these inverters respond as fast as they feasibly can, then even though in a strong system, one might see that if there is a step reduction in frequency, one might see a 200 millisecond delay in the response that's provided by these inverters. We can actually get good frequency response if you have good fast ramp rates from these inverter-based resources. And the maximum ramp rate that you see from these inverter-based resource is influenced by the characteristics of the energy source behind the inverter-based resource, which means that as you are getting new resources into the system to provide frequency response, you have to be cognizant of whether that's a wind resource, a solar resource, or a battery resource, because it can play a role in how you get frequency response from these resources in the time frame of interest, wherein if you can do only 2 per unit per second versus 5 per unit per second, if you have a lower ramp rate limit, you might need more resources to provide the frequency response that you want. Whereas if you have a higher ramp rate limit, which means a faster acting resource, you can need lesser number of resources to provide this response. So now supposing you had 4 IBR plants that are not providing frequency response at all today, and you want 2 new IBR plants to come in, the 2 new IBR plants have to take up the burden of the 4 existing IBR plants also, which means they may need to have a higher ramp rate limit in order to provide this response. So to close out, we can just summarize by saying that we need good, adequate simulation models for future planning studies, but any mathematical model in any software domain can be a bad model. It's important to recognize that if you have to parameterize these models with due diligence, we don't intend to mean that newer models can replace detailed studies. It just adds more tools to a planner's toolkit. And very important to continue the work with OEMs in order to keep this validation process as a continuous effort that goes on. And as you have new resources coming into the system from a frequency response perspective, the number of resources providing frequency response really plays a role in determining whether you will have good frequency response or bad frequency response. More number of resources reduces the burden on each individual resource, which means we share the burden of making the frequency response better for the system. So with that, I'll close out my presentation.
Thank you so much, Deepak. That was awesome. Thanks for giving that really important look at not taking things too simplistically, but really considering the nuances of aspects of models or what we're trying to get out of the system. So there were some specific questions that are related to what you discussed. One was asking if there are any documents available that provide guidance on how to properly tune positive sequence models.
Yeah, we do have material available on it, on tuning positive sequence models, model validation, and using event-based data to really tune these models. WECC has been doing a lot of work in that effort too. I'll be happy to provide those when we maybe circulate some notes for the workshop.
Sure, and I should add, there was a question asking about if these questions are going to be answered. And yes, we'll answer the questions and we'll circulate the answers to all of the participants following the workshop. I guess at this point, we should turn it over to the next speaker, and then we'll take the questions and have more discussion at the end. But thank you again, Deepak. That was great.
Yeah, no worries.
Great, Deepak, thank you so much for joining us, and we'll see you in the question and answers here in a little bit. We'll turn it over to Sebastian Kelly. He is with GE Energy Consulting. He is the managing director there. Sebastian, I'll turn it over to you.
Right, thank you. Good afternoon to everybody. This is lunchtime for the West Coast. And so I appreciate everybody that stayed this long. I work for GE Energy Consulting. We are a group of power system engineers that do system studies for companies outside GE and GE. And we also help GE businesses in relation to projects. My group specifically related to inverter-based resources like onshore wind, batteries, solar, and offshore wind. And we also get involved in aspects of design and verification of performance of the products. We are power system guys, so we mostly look at grid interactions. So my intention is to go over, try to contribute to the very good presentations that were done already from that perspective. And maybe I may be going over some subjects that were already mentioned, hopefully with a different perspective. Would you mind going to the next slide, please? So this is the outline. Initially, I will talk again about low system strength. I'm sorry you guys heard about this so many times. I will try to hopefully summarize some of the things that were said before and specifically try to articulate from our perspective where is grid forming relevant and where it is not. Also, this higher and better base resource penetration scenarios are affecting short cycle ratio. I think Julia mentioned several things about that. I would like to describe a little bit what we see in terms of the products that we see coming with respect to the products that are already existing and how those compare in that sense. Then the third bullet is to talk about grid performance aspects of grid forming, so where it actually differentiates from grid following maybe. And so where should we expect to see differences in performance and what problems is it actually going to most likely solve? The next bullet is related to why grid forming inverters are not sufficient to have a grid forming inverter-based resource. You see, sometimes we get caught in this thing that grid forming behaves like a voltage source, or we talk about grid forming inverse, like the only thing that matters. Not intentionally necessary, but as the manufacturer, we start worrying about other aspects that go beyond the inverter. And this may be helpful to address some of the questions about, can you simply change the inverter code and then you go from grid following to grid forming? So in what cases that's actually not sufficient? That would be the idea of that slide. And then I will talk a little bit about the battery projects. What did we learn from those grid forming battery projects? And I will briefly mention the grid forming wind turbine generator experience so far. So let's try to go through this. Let's go to the next slide, Travis, please. So low system strength again. I'm proposing here a separation of problems. So today, Nick elaborated quite a bit on this. I think Julia and Jason also touched on this subject in different ways. Low system strength challenges come in different flavors. The one on the left, or the one that the picture on the left is trying to represent, is when you have a large wind plant, a large solar plant connected at a point that goes through a very long transmission line, so a large impedance to the bulk power system. So if you look at the system strength at the point of interconnection of this new wind plant or at the combined terminals of the wind turbines, that system strength is low. In this case, we're trying to transfer significant amount of power with respect to that entitlement that Nick was referring to. So there's a limit that any source can transfer through that long transmission line. It doesn't matter if you're an inverter-based resource or a synchronous machine, there is a theoretical steady state limit. So these projects are trying to get close to that. And the low short cycle ratio, low system strength are indications that you're getting close to those limits. This problem is old. We've been dealing with this for a while. It doesn't mean that we're able to solve it all the time, but there is enough understanding on sort of limitations of different products to deal with this. This doesn't necessarily happen with a new project. In many cases, you have a number of projects, you start increasing the number of projects at the end of a long line, and at some point you start having these power transfer problems. And like I mentioned, so in general, the grid following industry has been designing controls, thinking of this type of problems for many years, maybe 10. Now, on the right, we see also a system that has low system strength. And this was kind of mentioned before, so I'm kind of repeating some of the things that were said. So in this case, you have an area that will be at the left of that WECC connection, where you have solar, wind plants, you add a new wind plant, you have loads, and you may have some synchronous generation, but the synchronous generation is relatively small in rating compared to the amount of inverter-based resources installed. And then, so all of this area connects through the bulk power system, potentially through a WECC connection. Now, I'm purposely defining this problem on the right as not a problem related to power transfer. It's not that you're trying to push too much power through the WECC connection. You just want to make sure that you can operate the system stably. Now, the system on the right is less frequent. We've seen the system on the left many times in different forms. That's a frequent problem. The problem on the right is a little bit more futuristic. It starts being observed in several systems, and definitely it is the expectation for many that if you install a wind plant today or a solar plant today, it will see high IVR penetration conditions like the one in the system on the right during its lifetime. So that's kind of the new problem in a way. Now, the aspects on the right that are not a problem on the left are related, for example, to angle fluctuations. So if you have a system that is mostly has inverter-based resources and is weakly connected to the rest of the system, the angle fluctuations that would tend to happen in this area will tend to be exacerbated if you have a large number of grid following inverters. As you increase this, you may start having angle deviations that are so large that equipment may start tripping. Similarly, there was a discussion about rock-off. The rock-off aspect is applicable when the complete system is getting weak. And obviously, there are aspects of system preservation, system operation, like energizing transformers, connecting loads, that make it challenging if you have grid following inverters on the system on the right, even though you don't have a power transfer issue. So I'm trying to differentiate these two. So the question that I'm posing or proposing is, what problem are we trying to solve with grid forming? So with that, if you don't mind, can we go to the next slide, please? So in the interest of concentrating now on aspects of steady state, fault and fault recovery performance issues, right? So let's concentrate on those two. We can simplify the system on the left with a little cartoon there that is similar to the systems that Nick was elaborating, and for the same reasons that Nick elaborated. You have that simple equivalent where you have a reactance. The reactance represents the electrical distance from the point of interconnection of the wind plant to the stiff source. And then we have the inverter-based resource. From the point of view of power flow, the green arrow indicates that all the power that comes out of the inverter-based resource is flowing through the reactance. And that's why this is kind of power transfer challenge. We're trying to transfer a lot of power through a large reactance. On the contrary, the system on the right and the little circuit on the right has a load close to the inverter-based resource, indicating, as it was mentioned before, that a good part of the generation or the power coming out of the inverter-based resource is being consumed locally in the load, and only a fraction of that is being transferred through the reactance, right? So these two systems, it's good to think of an example. So if we assume that both of these circuits will have a short circuit ratio of 0.5, that's a very low number compared to the things that we're typically discussing in the industry. So the short circuit ratio is 0.5. The reactance will be 2 per unit in the base of the inverter-based resource megawatt rating, for example. If we define a system like that, so the reactance in both systems will be 2 per unit. The system in the left, it just doesn't work. It's just not possible to push 1 per unit power through a 2 per unit reactance. There is no possible steady state point of operation where you can have the system working stably. So that's why the industry that is mostly focused on the problem on the left and it's very unusual to talk about short circuit ratios as low as 0.5. And it doesn't matter what type of IVR we're talking about, there is no possible way of operating that. The system on the right is very different. So if the reactance is 2 per unit, but let's say the load is consuming all the power that is being generated by the inverter-based resource, there is no power or very small amount of power being transferred to the reactance. So that system has a possible steady state point of operation, and it is possible for inverter-based resources to operate stably in a condition like that. There are plenty of details. It will depend on the controls of the inverter-based resources, the characteristics of the load, and several other details. But in principle, it is possible to get that system to work. So here we have two systems with same short circuit ratio, but have very different interpretations of what the short circuit ratio means. So in a way, we see that depending on what challenge we're looking at, this metric of the short circuit ratio may be misleading. Can we go to the next slide, please? So further elaborating on that, and continuing with the mindset of looking at fault conditions, all right? So we apply a fault in the system and we clear what kind of behavior would we see in the systems if we have grid following or grid forming. So the table there has several columns. The first column says load power in per unit. So that will correspond to the little diagram on the right, where the number 1 is related to the load, and the load will be in per unit of the rating of the inverter-based resource. The second column is the short circuit ratio, same way we discussed in the previous slide. And then we have the expected performance of grid following and grid forming and the different challenges associated to that. And here, there are plenty of caution statements. So on grid following, there are plenty of performance that can be expected. Different controls behave differently. So we're going to try to address that somehow, but any statement about if something works or not can be questioned. It could be applicable for one control, but not to another. And the same thing applies to grid forming. So there are some grid forming controls that behave differently than others. So it's hard to say that grid forming works for sure or doesn't work for sure. With that, let's look at the table. The first 3 rows have the load equal to 0, meaning we don't consume any load. And this is the same as the power transfer problem that we were discussing before, and that is mentioned in the upper left. If the short circuit ratio, say, is higher than 1.5, using the numbers that Julia was describing, we can argue about if it's a 1.5 or 2 or a number around that, but in principle, there is, for high short circuit ratios, it is expected that grid following and grid forming will have acceptable performance. There is a range of short circuit ratios between 1 and 1.5, for example, I'm postulating, where both of them could work. And this will kind of depend on the details of the control. To say that grid forming works and grid following doesn't work will be an oversimplification, because it depends on what particular inverter and product are we evaluating. But definitely, if the challenge to get that to work or not is related to power transfer. If we continue to reduce the short circuit ratio, we have the row with the load of 0 and the short circuit ratio below 1. It is clear, for the reasons we discussed in the previous slide, that grid follow won't work, and grid forming will also not work, because it's just not possible to transfer the power through that system, independently of what source does it, like Nick mentioned before. If we then look to the next set of 3 rows with a low of 0.5 per unit, we see that with short circuit ratio of 0.75 or higher, it's possible to get grid following to work. And this sounds like a contradiction. 0.75 is a very low number. We always say that short circuit ratio required for grid following to work has to be 1.5, 1. Well, but when we do those statements, we're thinking about the system in the upper left. If we have local load, that it is possible for several grid following concepts to work stably with short circuit ratios below 1, like for example, 0.75. And grid forming is also expected to work. As we reduce the short circuit ratio, we see a similar behavior as what we saw before with the load 0. There is an area where the power transfer is challenged, where both of them could work or may not work. And then if we go below what you can transfer through the system, it will just not work for none of them, grid forming or grid following. With that, let's get to the last one, which is we assume that the load is 1 per unit. So the load is consuming all the power injected by the inverter-based resource, and the short circuit ratio, let's say, is below 0.2. In that case, it's quite likely that the grid following will not work. And it's typically an expectation that the grid forming will work. So this is kind of the differentiation. The short circuit ratio is very low. There is no power transfer challenge. And here the grid forming is expected to do better. Now, it's a comment about the apple and the banana. So it's very common in the industry to talk about grid followings can operate for short circuit ratios of 1 or 1.5 and above. Grid forming can operate to short circuit ratio of 0. So those, one is an apple, the other one is a banana. So it is true that grid forming can operate with short circuit ratio close to 0, provided there is no power transfer limitation that prevents you from doing so. So if grid forming has a power transfer limitation, it will probably be constrained also for short circuit ratios close to 1, similarly to the way grid following is constrained. So in a way, I guess one of the main points here is that when we look at fault behavior and fault recovery, grid forming can operate for short circuit ratio 0, but only when you have a local load and power transfer is not an issue. If the system or application has a challenge of transferring power through a long corridor, then potentially grid following and grid forming may have similar behavior, with the advantage to grid following that has many more years of design and maturity. Now, the other comment related to the box below is this assessment of faults and fault recovery is what we're accustomed to do in the context of power transfer challenges, particularly for the first 3 rows. Now, when we look at grid forming, this is only a part of the things that we should look at, because the grid forming is supposed to differentiate with respect to grid forming, with respect to grid following in other aspects, not necessarily in this ones. Thank you. Can we move to the next slide, please?
Sebastian, we've got 10 more minutes.
Thank you. So the aspects where we do expect grid forming to do different than grid following is related to behavior to voltage jumps, response to rock-off. Like those 2 aspects were mentioned already. I'm going to go quickly through this. In principle, we see that requirements where inverter-based resources have to tolerate an angle jump without tripping. That's something that grid following and grid forming can do. The expectation is that grid forming would help the system by opposing to the angle changes. That's something that grid forming has a clear differentiation with respect to grid following. Rate of change of frequency is a similar concept and was described before. Regarding voltage control, I want to make one comment related to the last 2 bullets. There are concepts of grid following inverter-based resources that perform terminal voltage control, and that has proven to be very beneficial in low system strength applications. Grid forming also does terminal voltage control, typically, that's the expectation, with the advantage that it doesn't do it through a current control. So potentially there may be some additional advantages of terminal voltage control with grid forming with respect to grid following. But the bigger jump of advantages is a grid following IBR with terminal voltage control with respect to a grid following IBR without terminal voltage control. So there is a risk that in this discussion about grid forming, we get confused with improvements that you can have within the grid following concepts are mixed, like that is what the grid forming is going to solve. And voltage control is the particular area where that confusion could happen. Can we move to the next slide, please? Regarding the difference between a grid forming inverter and a grid forming resource. So a grid forming inverter, I mean in the sense that if you assume that an inverter has a perfect DC source, it doesn't matter how much power you extract or inject, the DC voltage that the inverter has is always perfect. It looks like the only problem or the main problem that we need to solve is related to the converter control within the current capability limitations of the inverter. Unfortunately, the problem is more complicated than that, because there is no infinite DC source. So the picture that you see down the left, taken from a paper from that Shruti Rao led, shows the differences in response to an angle change. So you perform an angle change in the grid, a voltage angle shift that could be, for example, because you operate transmission lines, significantly modify the power transfers. You can see that the grid following concepts basically do not modify the power output, and this battery has a significant increase in active power. That's the blue line, and that active power increase is very fast. that power and that energy has to come from someplace. So one of the challenges to have a grid forming resource is to have enough of that power and energy available in the time frame that is required. So in the case of wind turbines, like it was mentioned before, you can potentially use the drivetrain. So the drivetrain is rotating, there is energy stored there. You can potentially extract energy from there temporarily to do some of this. There are some limitations of doing that. You cannot exaggerate with how much energy you extract from the drivetrain without having problems of tripping on underspeed or potential torsional aspects related to the equipment. And the other ways of doing this will be with curtailment, which is painful, as everybody knows. We will try to avoid that, but that's another way. Or potentially, we may need to add hardware like energy storage someplace to take care of the fast power demands. It could be an injection and absorption. So to have a grid-forming wind turbine or a grid-forming solar inverter, solar resource may require more than just changing the inverter. And that is defined quite a bit by how much of this power, in the case of an angle shift, will require, for example. So the details on the requirements of what the grid-forming resource has to do will determine if you need to add more hardware or not. Okay, thank you. Can we switch to the next slide, please? Okay, let's speak a little bit about batteries. So in principle, the batteries have an advantage with respect to wind and solar regarding the availability of power in the DC link. And for that reason, I think that's one of the main reasons why we see that there are a number of applications of this. This slide was partially described before by Julia, so I'm gonna elaborate on a few points. So you did see, and she mentioned the 95 and 96 applications, and those were very helpful, but there wasn't continuity. There weren't customers asking for this after that. In recent years, we started this picking up more. You see the last 3 applications are almost in consecutive years. So there is definitely more interest now, and Julia explained the reasons for this particular interest in batteries for these applications. Now, the interest aspects of these applications are, although these are black start or gas turbine, it's important to understand that during the black starting of the gas turbine equipment, there is no gas turbine running. So this is really like black starting an industrial plant, basically. Because it's a black start, the short circuit ratio is 0. According to the banana terminology, not the Apple terminology. All of them require black start field demonstration. So you actually have to black start the system. There's no kidding. So this is not a simulation. You have to actually do it and demonstrate that you can start the system, and all these projects require that. And that's actually fantastic experience for us and hopefully also for the customers to make sure that this is working as intended. And the other aspect is that the solutions for this were modular, in the sense that you have small batteries and you basically add as many battery modules as you need, each one of them with an inverter, to come up with the rating that you require. So because of that distributed nature of the battery, the controls have to be compatible with having other sources close by. And for that reason, the control approach, this grid forming control approach that was used, is compatible with interconnected grids where you may or may not have other grid forming sources or other synchronous machines in the system. So that experience was very helpful in that sense. Can we go to the next slide, please?
I got 5 more minutes, Sebastian.
Thank you. So in these projects, we learned several things. The having to black start industrial loads has, for example, we did have to do direct starts of large asynchronous machines, and the pictures on the lower left show the battery output. So the power is the upper left and the reactive power is the upper right. You can see the significant solicitations to the battery. The curve looks like a typical motor starting simulation. It's just that in this case, all the effort of significant reactive power is being done by a battery. The handling of current rating was key to this project. Obviously, if you could install plenty, infinite batteries, this is easy because you're going to have enough current capability to deal with it. The challenge is how to do this with not so many battery and battery inverters. So the big learnings were about that, how to use the full rating of the available batteries, how to handle the current limitations without collapsing the system. That was an important learning. Energization of transformer, in general, we did soft energizations like Julia mentioned, but we did look into direct start of transformers as well, and that was part of the design. In general comment is that these grid forming requirements were very demanding. We had to be able to do all of these things with these little inverters. Now, you could argue that these requirements were too much for what is needed in an interconnected system. So the definition of these requirements actually are key to define the functions that you have and how to deal with the limitations of equipment. Can we go to the next slide, please? With wind turbines experience, it's very encouraging. So when you go from grid following to grid forming with a wind turbine, there are several things that change. On one side, it was mentioned several times, the inverter control will change. But then even how they convert the turbine and the plant controls are coordinated is different. So there are quite a few things that need to change, even in terms of controls. It's not only the converter control, the turbine control, and the plant control may also need to be modified. The expected higher frequency of fast active power fluctuations in the drivetrain is a concern. How to deal with that and how big are these power fluctuations is an aspect of design that is not well defined because the requirements are not clear yet. And then there are several of these grid forming performance aspects that benefit from overload. For example, if you have a rock-off event, it will be very helpful if the wind turbine can operate at higher than rated power, or similarly with reactive power aspects. The experience with the type 3 grid forming concepts that we've been demonstrating is very encouraging, and it has an advantage with respect to other concepts in terms of overload. So we're well underway with this. There is quite a bit of focus on lab testing for this because it's easier to test in the lab some of these extreme events than to test that in a grid, because in the grid such events are less frequent. So you kind of have to balance the two things. But demonstrations internally within our company and in some national labs like NREL are well underway, and we're very encouraged by that. The performance requirement definition continues to be an aspect that is not completely clear. Companies like GE and others are very committed to create products with grid forming capabilities, and we're working on it as the requirements are being defined, but some of the design aspects and the costs and how much you have to modify depend on the details of the requirements that are not necessarily clear yet. Can we go to the last slide, please? So first bullet, grid forming technology can support mitigation of several aspects of low system strength, but not all of them better than other stuff. Like not in everything grid forming will be better than grid following, or at least not initially. So the key differentiations for grid forming are system strength that are really low with local loads, that high IBR penetration scenario that I described, it was in the right in the slides before. That's a type of scenario where grid forming is expected to do better in terms of steady state stability, instabilities of controls, and surviving faults. So that's the strength of grid forming. The power transfer problem is probably not going to be better with grid forming than what it is with grid following. And then there are other important aspects that support for rate of change of frequency, support the grid for angle changes. Those are clear differentiations of grid forming. The grid forming performance options are really broad, and we as manufacturers are kind of very interested in defining products, but we need to help the industry and work together with the rest of the industry to define it. Battery grid forming applications were extremely helpful. We learned a ton. Batteries are easier in terms of grid forming than PV and wind turbines. PV and wind turbines controls are being demonstrated and progressing. We're very encouraged by that. And maybe I stick to the last point. The application of grid forming equipment, similar to the application of grid following equipment in low system strength, will have increased complexity and will require more complex studies, more difficult estimations, modeling will continue to get more demanding. So we look forward to collaborate with the industry in dealing with these problems, and we're trying to do our homework to be good citizens in coming up with products and interacting with customers to define projects. Thank you again.
Thank you so much, Sebastian. That was really helpful to really discern the difference in challenges between the apple and the banana approach, the high power transfer, and then the high inverter penetration challenge. So there's a question for you. Is your short circuit ratio table, so the banana apple table, also applicable for the composite indices, such as weighted short circuit ratio?
Yeah, that's a good question. So that page and that discussion in general was conceptual. I purposely avoided the subject of the composite short circuit ratio or weighted short circuit ratio. In principle, I would suggest to consider those short circuit ratio numbers as some form of multi-in-feed short circuit ratio calculation, like the weighted short circuit ratio or composite short circuit ratio. I think the use of the simple short circuit ratio calculation in the presence of more than one source of inverter-based resource, it's just not recommended. And I didn't mean to imply that. I think multi-in-feed concepts like weighted and composite short circuit ratio should be applied in all cases when there are more than one inverter-based resource plant.
All right, thanks. I think at this point, we'd like the other presenters to turn on their videos and their microphones so that we can answer more of these questions. And I know, first up, I think Julia wanted to answer the question about interconnection processes in ERCOT with respect to whether they consider in their connection planning studies N-0, N-1, what sort of criteria they use.
Yeah, the question was about WSCR when we were coming up with that value, if evaluation included N-0, N-1. So it was we tested different types of contingencies, N-1, but then WSCR of 1.5, it's like just a metric that was determined based on more detailed PSCAD studies, and then the metric itself is pre-disturbance, because we need to make calculation very fast in real time. So there is no time to recalculate for different contingencies. So in real time, it takes short circuit calculation that's based on actual topology at the time, and then actual production from inverter-based resources in that area. And as long as it's 1.5 or higher, then there is no limitation on inverter-based resources. So that 1.5 value is pre-disturbance, but it's determined based on simulating different contingencies in planning studies.
Great, thanks. And I think Jason wanted to add a quick comment on documentation for tuning positive sequence models, an earlier question that was asked.
Yeah, thanks, Debbie. And I saw the question come through, and Deepak answered it very well. I think this is a very relevant question about model validation and tuning, particularly with more features and functionality of inverter-based resources and even grid forming. That continues to be a subject that we build on in the industry. And certainly there's been reliability guidelines that NERC has published on the subject around tuning some of the generic models from WECC and tuning more specific models. But really the genesis of the model validation standards, the MOD 26 and 27, have long tried to get the tuning of those models to reflect equipment. And there is an exercise now going on within NERC to revise those standards and take into account more fidelity of positive sequence models when it comes to tuning relative to their behavior, not only during quasi-steady state, but also during disturbances. So I see actually there's a couple members of the drafting team. Jerry Thompson has joined us in the webinar, and we're continuing to talk about how do we validate the performance during disturbances and reflect that performance in the models for inverter-based resources, for fax devices, for HVDC, for conventional equipment as well. So just wanted to let people know that that's coming, and the subject around how models are going to be validated continues to grow in importance.
Great, thanks, Jason. So I think Sebastian talked quite a bit about how we can't just use SCR metrics in isolation, but one of the questions asks, how can we differentiate between strong and weak grids? Is the short circuit ratio greater than 5 the only way, or are there other ways to quantify this difference? So I guess, could you talk to the nuances of how we think about strong versus weak?
Yeah, so I think the actual relevant decision that you need to make when you're doing a project is, will the project work or not, in anticipation of building it. And at the end, what matters is are the converters that are being used in this system able to tolerate the particular system strength of the application? If you call that weak or strong, is kind of secondary, but I don't mean to dismiss the question, but in a way, at the end, what is relevant is, how does the short circuit ratio of the application compare to the short circuit ratio that is used in the performance verification of the product that you're planning to apply? That's one aspect that I will mention. So maybe what is strong and weak, for example, in the solar industry, may be different from what is strong and weak in the wind industry, for example. But the implication of that is secondary. What is important is, when you're applying a solar plant, is the short circuit ratio of the application in line with the way the solar plant controls were designed and tested and performance evaluated. That's one comment. A separate aspect that I think is very important, I'm sorry to repeat this, is that when things are getting more complicated, and we're having more and more plants close to each other. So you are evaluating your new plant, and now you have like 5 plants around it. They're not exactly next to them. They are far away, but not too far away. This is really challenging us, and I don't have a good solution for that problem. In general, the calculation of short circuit ratio, ignoring adjacent plants, is not recommended. That will give you a very optimistic result. So calculating short circuit ratio, ignoring the neighbor plants, and asking the manufacturer if that is okay, is potentially may lead to not detecting or masking problems. So it is necessary to have short circuit ratio estimations that contemplate the presence of plants close by. Now, on the other hand, what I am seeing as kind of more a consultant looking at system studies with this, is that because we're departing from the power transfer problem to the high IBR penetration, where we have mix of loads and several in-feeds, the short circuit ratio, like the weighted short circuit ratio, for example, is becoming too pessimistic. So it's still useful in the sense that you will calculate the weighted short circuit ratio, for example, for an application, and say, well, if it's less than 1.5, then maybe I need to do a more detailed study. But chances are that if the scenario is like this high IBR penetration that I described to you, 1.5 is going to be perfectly fine. It's just that at the moment, we don't have a good way of anticipating the risk as accurately as we were able to do with the power transfer problem, or we are able to do with a power transfer type application.
This is Nick. Can I chime in on that?
Of course.
Sebastian and I are very much in similar states of mind, although I like sometimes possibly oversimplifying it. I was trying to tease a little of this out with my use of the power angle curve, the nose curve, and the words that I used of entitlement. And I think I have no illusions that this is sufficient, but a piece of the puzzle that is important and fits with what Sebastian said, that quite honestly, we're not quite there, is making sure that the power transfer part, right? So Sebastian correctly pointed out that these systems are evolving, so it's a mix. It's not at the bookend of all transfer that I talked about. neither is it at the other bookend of Hawaii like. It's somewhere in between. But the idea that there should be some additional screening tools that are probably pretty simple, maybe PV curve based or PV curve with an asterisk where they're calculated, recognizing that the PV curves are actually dynamic, they aren't static things, would help us as an industry be able to screen for pre and post conditions that are too stressed or even hopeless, right? One of the truths of stability is if you ain't got a place to go, you can't get there. And all of us as consultants have seen problems posed that way. Or it's like, what? You know, we ran a simulation and it was unstable. It's like, yeah, there's no stable place to go. So at the least, as an industry, we got to be checking for those. And then I think we are on a trajectory over the very near term to start to understand some margins. You know, how close can the endpoint of the N-1 event be to the end of the nose curve, at the top of the power angle curve, and have any sensible expectation of stability? I think that is going to emerge as part of a new set of screening practice so that we aren't just stuck with, as everybody said very articulately, equivalent short circuit ratio is important, but it's not the whole story. So I think we're going to have a bunch of these things.
One other thing there, Nick, is with the stability aspect that you bring in, yes, definitely there's no place for it to go. So the end point of the N-1, but in a way, because everything comes down to controls and an inverter-based resource, it also depends upon when the fault cleared, at what starting point is the inverter-based resource starting from to then transition to the post-fault system, right? Because it depends upon that point also, if from there, can it move to the endpoint or not, which I know gets into a lot of control theory and stability theory and region of attraction and all of those things, which is not necessarily easy to evaluate because there's just many ways in which that can be done. But that's also one aspect that plays a role, that during the fault, the controls may do so many things which may take them to a position on your state plane. And then can they come out from that position when the fault clears will also be influential in determining post-fault stability.
I agree. I think Julie wanted to say something. If not, I have more to say on that.
Yeah, I actually had more to say about Sebastian's presentation and comments that followed. So I don't know what order is best.
Oh, go ahead.
Okay. Yeah. So I just wanted to point out that this, first of all, this, WSCR, this is just a metric. It's first for screening. And then it's an indicator of getting low. It's an indicator to do more detailed studies and figure out if there are any instability concerns there. And then we take this metric into real time because we have lack of tools in real time to do evaluation. So we just kind of find a safe 1.5 metric that we can use, but it's based on detailed dynamic studies, and then we use it in real time. That allows us to take actual real-time conditions into account. So that's one thing. And then we're also doing, to Nick's point, we're also doing, I guess we have both concerns at the same time, what was on Sebastian's slide about different flavors of short circuit ratio. If you have a long distance high power transfer, or you have a part of the grid that has a lot of inverter-based resources. So we have kind of both in panhandle area. So we evaluate both, we do voltage stability assessment in real time and that weighted short circuit ratio metric. And there are times when voltage stability constraint binds rather than that weak grid concern. So I just wanted to point that out.
Thanks. Nick, did you want to say something, or should we go to the cost discussion?
I think it's fine. Maybe just one last thing, and I think it fits with what everybody's been saying, right? We as an industry can't just use one tool. The really detailed tools, Julia showed how long it takes to run EMT simulations. There is a pathology that we absolutely have to miss, which is, only run EMT because that's the only thing you trust, and then you can only run 6 cases when you needed to run 6,000 cases. We can't do that. So we need tools to know when we can trust the simpler tools and tools that tell us when we need to dig deeper. And we're getting there, but it's a work in progress. That's all.
Okay, thanks, Nick. So another question is, what's the cost of a standard inverter versus a grid following inverter that has advanced capabilities like fast frequency response versus a grid forming inverter? So a lot of folks are interested in knowing, are you going to pay extra? And it may be different between a battery or a wind plant or a PV plant. I don't know who would like to.
You want me to? I could provide a view of that, an aspect of that. So really, if you have a grid following inverter-based resource and somebody gives you a grid forming inverter, you're probably not going to get what you need. So at the end, what you want is an inverter-based resource that has these features that we were talking about. The inverter alone can only do some, but it cannot do, an inverter doesn't have energy. So there are aspects of this that go beyond the inverter. So what is the cost of the inverter is probably not the answer is that you're looking for. The question is probably what is the cost of an inverter-based resource that is grid forming? And not necessarily that I know that answer, but I would say from the point of view of batteries, there seem to be options available that are not necessarily too much expensive than the grid following batteries, but then we get again into how much grid forming features or how many grid forming features do we need? What is the rating? What do we want this resource to do transiently? How much rock-off they support? Depending on all those questions, the cost will change. And all of those are grid forming. So in a way, there is a price for each one of those grid forming specifications. And I don't even know the price for any of them, but I would say in batteries is probably not too different from grid following. In the case of solar, to give the example of GE, for example, the second generation grid forming battery uses the same inverter as the solar battery. As the solar inverter. So the inverter is the we go again to the same subject. What are we going to ask this PV to do? If we're going to have to provide inrush of active power when it's operating and the MPP tracking operation, then we need a big battery, and that has a big cost. So the specification of the performance may drive significant additional cost in PV and wind. And that's not necessarily the case for batteries. I don't know if that helps.
That does. Does anyone else want to chime in?
Yeah, I just like to reinforce what Sebastian said, and maybe from a different perspective around the deployment of grid forming capability or even more advanced grid following with regarding how do you actually deploy it? And there is a cost associated with it, as Sebastian said. And as the requirements are being crafted, simply going after all of the features all at once in a huge step change is likely not the best way to deploy this new technology because of all the things you may have to do and the cost associated with doing everything all at once, right? So that's one thing as grid codes and requirements are being crafted for grid forming capabilities and technology. You may not have to solve every single problem in every single system, but if you're being required to solve all of those things all at once, it's going to be hugely costly. More costly than it would take to maybe resolve that one issue. So that's one consideration when trying to look at what requirements are needed. Do it in a step change fashion to solve the problem you're really trying to solve, not trying to coat this with a big blanket of requirements that would be very costly to implement and perhaps quench the deployment of the technology altogether.
Just that, Jason.
And sorry, to add to that. So, and in general, there is an intention to do that, right? So I don't want us to sound too pushy, because I did. The industry is trying to figure this out, and there is likely several things that you can do without significantly increasing the cost. Kind of finding that in terms of what requirements can be addressed without having to add a huge battery to the wind turbines, for example, or trying to find that as an important part of this exercise for us as an industry. So there is room for that, but we're trying to figure that out collectively. That's not something a vendor can do on its own, or something that a reliability entity can do on its own. So there is room for that middle ground of performance, like Jason was saying. It's not clear yet.
I think it also decides time to deploy, right? If you want one device to provide every service, then the time to deploy that device or that equipment will take more time, because it takes more time to design, develop, ensure it is robust. So say, for example, if we want every grid forming device to also be black start capable, then that's just going to take so much time to ensure that every grid forming inverter has the necessary resources, so to speak, to be black start capable. But if the goal is for 85% of the time in a 10-year operation, or 90% of the time in a 10-year operation, if the goal is to be stabilizing the region of the network from which you can extend the number of inverter-based resources or keep it more stable, then that resource doesn't necessarily have to be grid forming with black start capability. And it can be grid forming in a different manner, just so that it can improve the stability of that region.
Sure, that's great. Thanks, Deepak. There's some questions relating to stability and controls. William asks, how does an IBR identify when to provide inertia? And John, and asks this from BPA, asks, how can IBRs contribute to angular stability, since inertia helps reduce how much the two parts of the system move apart from each other? I don't know.
Shall I jump in first?
That's great, Deepak.
I mean, I think those questions are very relevant. I'd like to probably suggest a minor change in not using the terminology of inertia there, but rather energy injection in a fast time frame, because that's what inertia is from a machine. It's an almost instantaneous injection of energy. And then now you can have IBRs that, so let's take the second question first about systems moving further apart during a disturbance. Yes, the angles in a machine move and they change and whatnot, and then they're synchronizing torque and all of that. But from an IBR perspective, if you start injecting current in a fast and timely manner, and it could be active power current, it could be reactive power current to control the voltage so that you prevent the spread of the angle, then you can bring about an improvement in the response of the system. So it's all about that fast injection of energy in the timeframes with which we are talking about. Now, yes, there is a component about how does the IBR decide to inject this. Some of this could be through certain control schemes like how Sebastian showed, where it can be brought about to be more of an inherent response where you don't control the current that much. Some of it can also be through, if you do control the current, you can decide how much current to inject based upon how your angles change or based upon how your frequency changes. And then you can utilize that to control the amount of current being injected and improve the response of the network. With that, I'll step down.
Thanks, Deepak.
I just want to add a little bit, just looking at it kind of from another angle. It fits with what Deepak just said. The example that I showed, if you want to think of that, that was a very basic or relatively basic grid following control with, in the language of our industry here, is zero inertia for the wind turbine. And in that case, a nice way to think about the response in the event that I was showing, which is obviously not all stability events, is that the control chases the angle of the rest of the grid with essentially without the baggage of having to drag the inertial energy along. So the point of that is that from a stability perspective, inertia is a two-edged sword. So it is absolutely not a fact to equate more inertia with more stable. There are aspects of inertia that are beneficial from a stability point of view, and there are aspects that are not beneficial that frankly we spent a century learning to put up with, not because they're good, but because we were stuck with them. So that requires a little mental gymnastics. Okay, I'm off.
I have a short comment, and I'm sorry, I got disconnected when Nick was speaking, so sorry if I'm repeating something he said. So on the first question of how does the inverter-based resource identify when to provide the additional power, I'm going to mention something that is very basic, but in principle, these control actions, like Deepak was saying, are intended to be really fast. So this can only be done based on signals that the converter control is receiving. So the feedback signals for the converter control are all the information that are used to make those decisions. And the intrinsic algorithm of the control in grid forming is more responsive to variations in the angle of the voltage than it is in a grid following. But the information is all based on the voltage and current measurements. That's all. And it is a control, it's a control response, it's just that it's controlled differently to make it faster in case of grid forming with respect to grid follow. Regarding the areas apart, the comment I would add with respect to what I think Nick was describing is that in a way the angles go apart because we keep pushing power when the system cannot take it. So it's a very, so during a fault, if you push too much power, also like Nick was describing in his presentation, the angles tend to grow apart. But it's a very common practice in the industry now for the inverter-based resources, either grid following or grid forming, to identify the conditions in which the system cannot really take too much power and reduce the amount of active power.
Oh, Sebastian, you should turn your video off. Okay.
I think he was close to the end of his thought. He and I have talked about this at great length. So let me just make a quick final point, and that is this: what he is saying is one of the pieces that goes in the controls for weak grid applications, and it's a piece of what the truth according to Nick. You cannot stuff watts into a sick voltage, and so weak grid controls are sensitive to the fact that the system isn't accepting the watts and will reduce the power. That is a tremendous virtue, and one of the reasons why grid following and grid forming are in many regards more stable than synchronous machines. Okay, I'm done.
Thanks, Nick. So here's a question that's a little higher level. How do we communicate with ISOs, transmission owners, gas generation owners about reliability issues that grid forming inverters can address? So how do we bring some of this information out to a broader audience to understand that there are technologies and mitigation options that can help address different reliability issues? What do we need to do?
Send the link to this webinar around.
Yeah, I was about to say.
We will definitely be doing that.
Well, there is a ESIG high penetration of inverter-based resources task force. We're working on a white paper that digs deeper into what's grid forming, what's available, how it's incentivized. So some of the things that we were talking about today, and we are writing a white paper that's about to come out by the end of the year, hopefully. So that's another way, I guess, like industry coming together, putting their heads together and sharing the experience from manufacturer perspective, system operator perspective, researcher perspective, because I think we all have different understanding of what's grid farming and what's not, and what's needed for the grid as well, and how it needs to be achieved. And so I think we need to solve it together and disseminate this knowledge. That's all.
Excellent. So those are some things that people could look out for as probably something that'll be posted on the ESIG website, maybe the end of the year, beginning of next year. And also, a lot of folks referred to Julia's article in the IEEE magazine.
That was a combined effort of a lot of smart people that Julia led, let's say that.
That'll be coming out to IEEE members probably in the next month. So those are some avenues of disseminating this information.
Yeah, and I just add to that, there are many forums right now. Certainly ESIG is a big platform for discussion on this, and we've got a lot of great contribution. But NERC as well, with the IRPWG and activities that are going on with, looking at the reliability aspects and how that should be disseminated is another good one. But I think the really important thing is that because of the change that's happening that we're experiencing now, there has to be more participation from all the stakeholders, from the regulators, the utilities, the ISOs, together with the developers and the OEMs on how to figure this out together. It just can't be done, ISO separate from equipment owner, separate from OEM anymore. It really needs to happen in a very succinct manner all together to figure out requirements and deployment of technology. So it really, my plea is to get engaged, get involved in a lot of these activities, because it's very important to hear all the perspectives on how to make this work.
I can say something snarky too here since I'm the grouchy old guy. As an industry, we also have to police the laggards. There have been incidents in recent memory that will go nameless, in which most of the participants in the industry have done their part and recognized their obligation to keep the grid reliable, and a few participants that think that the business of supplying electricity is the same as having a bank account and doesn't require to be good citizens. And I, for one, find it infuriating to have a few bad apples soiling the bucket. So straighten up.
Thanks, Nick. I guess we should also mention the DOE Unify consortium that Deepak and G are part of, that will also hopefully be doing some of this outreach to various folks. So I'm sure people will be hearing about that as well. So I'm realizing it's at the top of the hour, actually past that. And I personally would just like to thank all of our speakers for their presentations, for educating us, for thinking very deeply about how this is going to work and the power system of the future. And also thank all of the participants for hanging with us for 4 hours. As I mentioned, we're going to have the answers to a lot of these other questions that I'm sorry we didn't get to. We'll have those sent out around to participants by email, and everything's going to be recorded and posted on the WECC website. Travis, did you want to?
Debbie, thank you so much. Thank you again to all of our presenters. I'm just going to echo, Jason, Julia, Nick, Deepak, Sebastian, thank you so much for joining us and taking time out of your busy schedules to share with our attendees. And again, to the participants, thanks for joining us. As Debbie said, we will be providing a recording of the webinar. I'll also attach the PDF of the slide deck that you saw today that you can interact with, and we'll be answering those additional questions that we we're unable to get to. But again, just want to say thank you to our panelists for joining us. And
Yeah,
have a
Travis,
great
and
day, everyone. Oh, go
yeah,
ahead.
before we go, I'd like to echo the same to both Debbie, Deepak, Jason, Julia, Nick, and Sebastian, and everyone that dialed in today. And the question you asked, Debbie, about how do we reach out and get people involved in understanding these issues, I think spot on with this type of activity. More and more of these types of activities, the work that ESIG does on your workshops and your training sessions, this is the kind of outreach that we need to do. And I know that our energy storage task force, we're trying to get together the end of the month and try to relook at the focus of what our group should be doing, and should there be some form of restructuring of our energy storage task force, and a relook at what work do we need to do, what is the future work. So hopefully we can get more stakeholder engagement in that process. I think that's what's critical here in WECC. But I really appreciate everything you guys did today. It was fantastic. Just a tremendous amount of information shared.
Absolutely. Well, Steve, thank you so much for that. Again, to our presenters, thanks for joining us. And to our participants, hopefully you can join us in 2 weeks for our Reliability and Security Digital Workshop. You can go to WECC.org for more information for that. And on that note, everyone have a great day, and thanks for joining us. Take care.